नाम वित्रयवतु गणेशाय नमः सरस्वत्यै नमः श्रीगुरुभ्यो नमः हरि ओम् सहनावतु सहनौ भुनक्तु सह वीर्यं करवावहै तेजस्विनावधीतमस्तु मा विद्विषावहै शान्ति शान्ति शान्तिः ब्रह्मविदाप्नोति परम् तदेशाभ्युक्ता सत्यं ज्ञानमनन्तं ब्रह्मा यो वेद निहितं गुहायां परमेभ्यो मन् सोऽश्नुते सर्वान् कामान् सः ब्रह्मणा विपश्चितेति तस्माद्वा एतस्मादात्मना आकाशः सम्भूतः आकाशाद्वायुः वायोरग्निः अग्नेरापः अग्न्यः पृथिवी पृथिव्या ओषधयः ओषधीभ्योऽन्नम् अन्नात् पुरुषः समायेष पुरुषो नरसमयः तस्येयमेव शिरः अयं दक्षिणः पक्षः अयमुत्तरः पक्षः अयमात्मा इदं पुच्छं प्रतिष्ठा तदप्येष श्लोको भवति ॐ शान्ति शान्ति शान्तिः
Om Shri Sai Ram. With utmost reverence, I offer my humble pranams at the divine lotus feet of Bhagwan Shri Satya Sai Baba, the founder chancellor of Shri Satya Sai Institute of Higher Learning. Distinguished speakers, esteemed senior faculty, respected colleagues, and dear students, Sai Ram. It is both an honor and privilege to extend a warm welcome to aloe vera plant, which symbolizes sustainability. Thank you, sir. Sai Ram. The first day of the symposium brought invaluable insights into the transformative potential of chemistry in addressing some of the urgent global challenges of our time. We were treated to a series of thought-provoking talks and discussions that showcased how chemistry serves as a catalyst for addressing some of the most pressing challenges of our time. From advancing green technologies and carbon-neutral processes to pioneering solutions for resource efficiency and environmental conservation, yesterday's sessions were not just informative but truly inspiring. They underscored the crucial role of chemistry in bridging the gap between scientific innovation and real-world application. Today, as we embark on another day of stimulating dialogue, let us carry forward the momentum built yesterday. Together, we will delve deeper into the ways chemistry can serve as a bridge between science and society, offering solutions that are not only innovative but also impactful. As we continue our exploration of sustainable practices within academia, It is my distinct honor to introduce our upcoming panel discussion titled Implementing Sustainable Practices in Academia. This session brings together a distinguished group of experts who have made significant contributions to environmental sciences and sustainable chemistry. Professor Vinayak Sinha, Department of Earth and Environmental Sciences, IISER Mohali. Professor Chandramouli Subramaniam, Department of Chemistry, IIT Bombay. Professor Venkata Krishnan, School of Chemical Sciences, IIT Mandi. Their collective expertise encompasses a broad spectrum of sustainable practices, and we are privileged to have them share their insights with us today. Please join me in welcoming our esteemed panelists as they commence this significant discussion. I request the panelists to come take their seats in the dais. Thank you.
Humble pranams at Bhagwan's divine lotus feet. Uh, so today, this morning's session, I think we discussed yesterday that it would be really nice to have the audience take the lead in guiding and asking and making use of this session. I'd just like to start by inviting the panelists to make a few introductory remarks, but then really we would like you, Venkat.
Yeah, Om Sri Sai Ram. I hope I'm audible. Oh, is that fine? Yeah. The title of the panel discussion is Implementing Sustainable Practices in Academia. So this is a very broad title, and because sustainable practices are really very important in our everyday life, and especially given the fact that we are all in academic institutions, and in academia, how we can implement the sustainable practices. So I would like to categorize this practices into three different categories. So mainly how to implement the sustainable practices in terms of the teaching, and in the second in terms of research, how we can implement the sustainable practices, and thirdly in pretty much everything which is connected to the academia, like serving the institute, doing some administrative work, and various type of activities which we are a part of, both curricular and co-curricular and extracurricular activities, how we can bring in the sustainable practices. So first I would like to touch upon the research, because as teachers and researchers, we are most of the time we are involved in doing research activities. So how we can bring in sustainability in research, and as chemistry students and chemistry faculties, so we always need to think about the sustainable practices, like whether our practices are long term, are we leading to a circular economy, And is there any wastage which are involved, or how the wastage could be minimized, and also the energy consumption, how it could be optimized, so that the processes are all sustainable. So some of you might have attended my talk, or pretty much all of you would have attended my talk yesterday. So one of the things which particularly in our group which we are trying to do is having some self-imposed constraints on whatever the things which we are doing. It's kind of bringing in some sort of a discipline in terms of the research as well. So for example, our group is working in the area of catalysis, and in catalysis how we are bringing in some sustainability, like we do not want the temperatures to go beyond 250 degrees centigrade for any of the reactions, and also to have non-toxic, green, and pretty much renewable solvents and resources for the doing the chemical reactions. So these are some of the examples of how we can bring in some self-imposed constraints and try to achieve the sustainability to the best extent. Obviously, 100% extent would be too difficult, and perhaps it may not be feasible, although the aim should be that, but how maximum we could try to bring in the research. So whatever is the field of research you are working on, think from that angle that is my research practices sustainable? Are they optimal? Does it involve any unnecessary wastage? Wastage would involve the solvents, the chemicals, and so many different things. So that is one thing in terms of the research. And second, in terms of the teaching, also the teaching practices. Although I am relating this word sustainability with the retention ability as well, like whenever you are listening to your teachers, and or you are reading from books and acquiring the knowledge, think from that angle that how much of this knowledge is getting into my mind, and how much I could make use of it in the long term future. So that is also some sort of a sustainability which will brought in terms of the teaching. You might be studying some courses in green chemistry and also sustainable chemistry and all. So think from that angle that how the teaching and learning experience could be sustainable. And also as students, you also think that whatever you are learning, can we kind of carry forward to the next generation, or you can teach some school students, or you can teach some other your family members. So you kind of develop that habit of not only acquiring the knowledge but also the dissemination of knowledge. You are sharing your knowledge with the people. In that way the knowledge also grows, and the perpetuality would come through. Just before some time we have listened to the Vedas. This has would be perpetuated over multiple generations and throughout. And thirdly, in academia, most of us, especially the faculty members, are involved in a lot of different administrative works and many things. And how we can bring sustainable practices. At least from IIT Mandi perspective, when I was the dean, we kind of came up with this principle that we will operate as much paperless as possible. So every request would we created some portals where the things would go through an office automation type of a system, where the things are done very quickly. It requires minimal paperwork or almost no paperwork, and everything is managed electronically. In this way, the carbon footprint is drastically minimized, and there are no paper trails which need to be there, and things can be done in a much more efficient and fast way. Otherwise, just for one paper to move from one office to the next office, it will take quite a long time, because the peon who is supposed to move the paper is on leave or some sort of a thing. So those type of excuses will not happen. And if it is electronic, you can handle it at any point of time in a much easier way. And right now even many of the journals and all are also adopting the same type of a strategy, wherein you submit your papers online, and all the processing and everything are happening electronically. So in this way, even in some administrative matters, one can bring in the sustainability in the sense you can minimize the paper trails and unnecessary emission of carbon into the atmosphere. So these are some of my initial thoughts to begin with, but I'll be happy to answer any further questions if you have, because we would like to listen more from you, and also to learn from we would like to learn a lot from you all. Yeah, thank you.
Thank you, Professor. Now, Professor
Om Sri Sai Ram, offering my humble salutations to the Divine Lotus Feet. Um, Venkat brother has covered quite a lot of points. Um, but uh, so what I'll try to do in the next 5 minutes is try to look at sustainability as a wholesome concept, not try to break it down into what chemistry can do, what physics can do, or what biology or materials or maths can do. That I feel might be a simpler but insufficient solution to the complex problem that is sustainability. Um, so uh, when you look at sustainability, I'll try to first start by giving a few examples what we have done at IIT Bombay at a institutional level, which I feel are certain good practices that can be shared. Again, sharing can help. The idea is that sharing of these concepts or ideas can be help to grow sustainability in other campuses, including our own institute. Um, we have there is a group in IIT Bombay which is called Green Energy and Sustainability Hub, which is like faculty from a lot of departments collected, about 10 of our faculty members. This is now an official group which looks into the entire sustainability of campus. The idea is we treat the entire IIT Bombay campus as a living lab and try to experiment on the campus itself. So the campus is our laboratory. So you try to experiment and bring about greater sustainability on the campus. Of course, there will be a few failures, like just like how we do an experiment in the lab. Not all experiments would have end up in a success. But the idea is, if you treat the campus, it's a IIT Bombay is like similar to Parthi. It's a residential campus, so the students stay on the campus. Most of the faculty also stay on the campus. So that way, there is a good variety in the spectrum in the kind of people you would encounter on the campus. So there'll be students at undergraduate, postgraduate, PhD levels, and faculty, our families. So there'll be a huge spectrum of people that you will encounter. So then, if we can try to, with a few hits and trials, try to uh, develop. Something we did was the Green Energy Sustainability Hub, the GESH, like what we call it. The first thing we tried to do was look at energy consumption, because how do we bring in more energy efficiency, or in particularly in the context of our electricity, say so as to say electricity bills. How do we reduce our electricity, given that in India most of the majority of the electricity comes from the grid, which then means that it is largely inefficient and also dumps a lot of carbon dioxide and other problems to the environment that we are living in. How do we cut down our electricity bills? So for that we have done two things. One is all the fans in the entire campus is now replaced with BDLC fans. So the conventional fans that you see here are now going, it typically operates around 150, 200 watts of power, and we can, if we replace them with BDLC fans, they would need 75 watts. It's one single step that cuts down the energy bills by 50%, and therefore there is an associated CO2 footprint that can be calculated, that is also brought down. And this is, and we are actively doing this entire every single fan in the campus within a space of next 2 months is going to be by before March. We have given ourselves time till March 31st, is going to be run on BDLC technology. The other thing is the major need 24, and other times, if at all, because instruments require, if not for humans, facilities, instruments, sophisticated instruments do require air conditioning, and so that is, we can't avoid that, but at the same time we'll try to minimize that. The third thing that we have done is for water. We have now implemented complete water recycling policy. So all the wastewater that comes out is now, we try to kind of purify it and reuse it for our own inside the campus. So it's basically, we are not throwing wastewater out, but rather using it for other things like, say, for example, gardening, things that don't require pure water. Construction is one such activity, because construction requires a lot of water, and this water can be mid-treated water, so-called you take the brackish water out and then you treat it to a certain degree, and then it is kind of probably not definitely not usable for potability, for drinking purposes or cooking purpose, but you can use it for other things like gardening and things like that. So that also comes down. Water and carbon footprint has a very strong correlation, so we are trying to cut down on that. And the last thing that we want to do is, we have already done with the help of the director. Our director, who is also a very supportive person, is cut down on single-use plastics. So we have banned single-use plastics throughout the campus. So these are some of the initiatives I'm sharing with you, with the idea that whichever is kind of suitable, you think is suitable for you, you can take it forward. But we have done or in the process of doing all this, and already we are seeing a change in our surroundings, in our environment. So I thought that is what I would try to put forward. Thank you.
Thank you, Professor Venkat, Professor Subramanian. I think this sets a very nice tone for the discussions. And since many of the points have already been covered, I'd just like to make two very quick points before opening the session to the audience. One is that when we talk about sustainability, my impression is that this is nice that this is a word that now different disciplines and communities are, the awareness has grown and are taking active efforts to implement and incorporate it. And some of those were mentioned already. But we also have member of the society to be able to live a sustainable life. Now, in the context of academia, what comes to me from my own personal experience, thanks to Bhagwan's grace, is that I was able to get the opportunity to study and have one of the best quality educations in my undergrad and masters, thanks to great teachers and this institute. And that was possible because I could access it. There was zero fees. I didn't have to pay a single naya paisa tuition fee. And now one of the biggest challenges in terms of sustainability is not really so much about do we have the cleaner energy portfolios to switch to, like solar power, wind power, renewables? Do we have the technologies to clean up the environment like many developed countries have done in certain parts of their country, the region? The biggest is the inequity that exists between the have and the have-nots, the poor and the rich. And surprisingly, despite the GDP of many nations growing, it's if you look at whether that GDP growth has evened out the access to education, the access to quality. So where I'm coming from is very practical. Suppose I'm a person who has to cook something or has to keep my house warm. I need energy, right? For that, I use a fuel. Now, if the clean fuel is something that is unaffordable, even if I do not like it, I'll be forced to use the dirty fuel. Similar thing pertains to waste handling. So my point here is that institutions like Sri Sathya Sai Institute of Higher Learning have already shown the way in how, by enabling individuals like myself who probably would have not been able to afford this quality of education, by providing free education, we are evening out and reducing the gap between those who are under challenged in terms of means to access the best that society has to offer. So every day in our whatever we later on do in our careers, life, or even starting from today, if we can look at somebody who does not have the same privileges that we have and try to improve that, I think, as was already mentioned by my eminent panelists, try and support and help that, nurture that. That is the way forward. Otherwise, we may have these nice concepts. Otherwise, we may have isolated pockets where this works well. Like recently, if you talk about the air pollution in Delhi NCR, the rich bungalows, the rich societies, they all came up with their own means to insulate themselves. I don't think that's the way forward. As I said, everyone is safe, or everyone will be safe only if no one feels unsafe. So similarly for sustainability, we do that. Now coming back to the other second point quickly is that in addition to all these very, very important practical measures, one thing that we can do is we all use a lot of RO water systems. And at least in ISER Mohali, we made a very conscious effort that, the rejection ratio is set at a level where you actually do not deplete the water that you're drinking of the essential minerals. Okay, you clean it up, but at the same time you don't deplete of new. And the reject water is very, very useful and very good for irrigation, because it's actually rich in many of the other substances which we do not want to drink. And so we consciously, at least at home, do that. Another point that I think is worth mentioning is composting. You would see that there are trees on our campus. There are these leaf litter. This should not be burnt. This should actually be composted. And I mentioned in yesterday's talk that cow dung is very bad to use as a fuel in a cook stove. But cow dung has a very good use if you use it as manure and as also starting material to kickstart your biocompost. In fact, the technology is so mature. On Amazon, you can nowadays order these drums where you get your biogas production working with, if you have a steady supply of cow dung and manure. So, and traditionally, if we look at Indian architecture and Indian technology, so all of these, by the way, solar mission, the government of India is doing a very good job in terms of promoting this. We as individual members have to also be the change. And last point is, therefore, this means that whenever, like Swami used to say, there's a big problem, there's also a big opportunity. Often what happens is when we are overwhelmed with all this, how mammoth the task ahead of us is, there may be a tendency to get depressed and that, okay, it's probably very gloomy and hopeless. No, this is actually a great opportunity for you all, the younger generation, because today, if you look about the environmental sustainability sector, chemistry, physics, mathematics, as sir was saying, interestingly, for human development, right, for all countries, every country now is pouring a lot of their resources into making this happen. So there are lots of opportunities, and I hope you all can ask about those now. So with that, we'll, as panelists, stop here, but we'll be happy to answer questions to the best of our ability. And also, we welcome the experts sitting in the audience to please help answer these questions. So, brother, could we have somebody who could take the mic? So please feel free to ask any and every question. You can see that the breadth that was mentioned here is basically everything under the sky. So any questions in terms of what you have seen? Yeah. Yes.
They are very precious. So now we should also think of how to practice whatever is mentioned by you all. Of course, as Professor Subramaniam said, IIT Bombay is practicing, and months ago when I was at IIT Bombay, I was seen it, and we had the sodium ion battery conference, and it was very good
Yes, thank you, ma'am, for the wonderful inputs. So yes, like I said, from whatever there are, these are just a few practices we have done. In fact, our director sometimes commutes from outside Bombay and outside the campus, and so whenever he travels, he makes it a point to he's constantly calculating his carbon or put in for what is our footprint, basically carbon footprint on the campus. And related to one point that brother Naik said, the RO water usage. So there are just I wanted to quickly point out two things. One is the RO reject can actually be used for other purposes. The reject water from the RO, if you have a large RO plant working, the reject from that, which is roughly about 50%, on a good day, it can go up to 60-70% reject also. That can actually be used for several other activities where portability and drinking is not required. That is one thing. And the second thing is the again on at a departmental level, one of the other things that we are doing is separate out the batteries. The used batteries, can we collect them? And there is actually we are trying to set up a recycling center where, like what ma'am focus, spoke about yesterday, presented yesterday, recycling the batteries to actually at least have a second level of, it might not be the best batteries, but it will certainly be helping to a great extent to hold the material and give it a functional form, even if it is a slightly lower functionality. So these are there are already startups in this domain which are working in this battery recycling. So they would be actually happy if you can kind of segregate the used batteries and collect them throughout the campus. They will actually be happy to buy it from you. What we see as waste or throw it out can actually become wealth. So that is these are the 2 points that I wanted to bring in. Yeah, but more from the and probably one thing we can like just my thought, speaking of the top of my head, a small student led sustainability cell can be formed in the campus, which can look at what are the possibilities which can happen inside our campus, such as SSSIHL. And if any kind of input or support is required, I'm from IIT Bombay side, I'm more than happy to do it. So that is something which I want. Thank you.
Any other questions? I see some interest there. Yes.
Sairam sir, can you discuss any breakthroughs in development of sustainable chemical products or process that have potential to change industries?
I'll just quickly make a very small statement. Just wait for my talk.
Okay, yeah. Yeah, that's a good thing. You can listen to his talk to get to know more. Industry practices, so we can kind of do not just a small thing, but a revolutionary change in the way the industry thinks and operates. The industries mostly focus on the profit and its margin, mostly. But if the industries nowadays the industries are also having certain requirements of the sustainability, they have to contribute to the circular economy, corporate social responsibility, and many things. So in this regard, the industries can think about how to make their processes green and more sustainable. Like yesterday, sir was also talking about the Haber-Bosch process, and people are actively looking for the replacement of Haber-Bosch process, or even to kind of not only the Haber-Bosch process, but many other industrial processes wherein the industries are known to be using some toxic solvents, or the processes which are energy intensive, like high temperature, high pressure type of processes. But the same thing can be also done at a much lower temperature, at lower pressures, with a much lower energy requirements. Although the industry may not immediately switch from a known domain to an unknown territory, but nevertheless there is a lot of scope that many of these industry processes can be made more green and sustainable, and some industries are already working in this regard. in collaboration with the academia, and also they have their own R&D units wherein they are working in this regard. So it is possible, but it should be a collective effort. And academia can substantially contribute to this by collaborating with the industries and making the industry.
The perspective here is that, as sir rightly told, it's cost, but the way industry drives its, itself is through margins. So we will talk about in my talk about how margins are decided. And if you talk about, like, today I'm earning, say, on a given product which is made for 50 rupees, and I want to make 100 rupees over it. In the future, I would love to make 110 rupee or 120 rupee. We want to grow. We want to make more money end of the day. And there are two routes to do that. One route is, okay, I make an awesome, fantastic product which can be potentially sold for 300 rupees, and still I can make it for 100 rupees. So I have a increase. But the world is not going this way. Much of it is driven by, politics, by how relationship between two countries are there. Today, everyone knows there is a Russia-Ukraine war, and then the world is split. You have the Israel conflict going on. So oil prices are tumbling in different regions. So the perspective is that today, in today's like current scenario, much of the industry wants to lower its cost. And people still want to maintain that profitability. So the profitability drives the way you make your products. End of the day, you have to reduce the cost at which you are producing things. So if we were making things at 50 rupees, tomorrow we want to make it at 40 rupees and make that 110. So that's the drive. Actually, we are talking a lot about sustainability, future, everything. But I can tell you, in market, it's all about that fact that you have to bring down your cost, you have to increase your profits, and that drives the market. And there are 100 things going on around the globe. I'll talk about maybe 3 or 4 of them. But every company today does that. Reducing material. Just I give you a small example, as you told. So in the past, all the cars were made with steel. The drive today is plug in more and more of aluminum into it because you make the cars lighter. When you make a car lighter, you will use less fuel. So all that can be translated into, oh my God, we are using less fuel, we are becoming very sustainable. Hindsight, there is also one more fact. To process aluminum, it's much cheaper than to process a steel car. So you have lighter car, and a lighter car can undergo even more accidents than normal. So people say that, we used to drive Ambassador car. You cannot do anything with Ambassador car. Like, it's that rock solid. Take a BMW or Audi today, you just, go next to something and it will crash off completely. So there are always pros and cons, but end of the day, with aluminum, you are reducing the cost of production also significantly. That means you are making more profit than before. So it's a perspective, end of the day, how you look at it. And I would say that the world today wants to, increase their margins, their profit, despite what conditions are there in the market. And that is driving all these goals, what we are talking about. Anyways, we discussed during the talk.
Is there a need to start a department of, say, sustainability or a center for sustainability in every university?
So I would say that, see, rather than thinking of a department or a center of sustainability, because sustainability is such an interdisciplinary topic that what probably can be done is, if already departments are existing departments, you can pull out people and create something like a smaller working group or a center.
Or maybe a student club?
Student club. You can start with a student club. That's what I was kind of suggesting. The student led activity, I have always seen that student led activities are always more driven and successful. So, and a center organically emerge. So different faculty from different departments can would be interested in contributing to the sustainability activities through this cell, and so they get associated naturally with the cell. Then it grows now organically to make a center. So rather than kind of artificially starting with a center, if it can grow by itself, that will be much more effective, is what I feel, sir.
So, any other questions?
Yes, sir. Sir, Sairam, and thank you for your valuable insights. Sir, I have question based on Venkat sir's opinion. He had been saying that we can shift to electronic way of dissipating the information and other paperwork. But recently, I have started taking environmental science classes for our first UG students. That's where I realized that even the server-based cloud servers that we talk about actually are much more energy intensive than just the paper that we drive. So can you give little more insights, because you have been in the field? Maybe you can add one stat that we came to know is just a Gmail accounts that we all use is almost equivalent to 7 million cars more than currently what the globe has. So I don't know how to balance this out. Maybe you can throw some insights on this.
Yeah, that's an excellent question. Yeah, in fact, there are also the carbon emissions due to the electronic usage and how these things propagate. There are a lot of surveys and studies in this regard. So that's some one side that's there. That's true. But on the other hand, if we think about the paper trials and also the maintenance of the paper copies, because earlier at IIT Mandi we have been, and even till still also for some of the things like especially the bills and all, after we get and process those bills, we maintain a scanned e-copy for better usage and for the easy maintenance and all, because we cannot go back and look at the files easily, but we maintain a e-copy. So the electronic trail is anyway getting created. So if we can kind of instead of having the paper trail plus an electronic trail, if you can go with only the electronic trail, that will be advantageous. That's the point which I kind of wanted to highlight. And also when we see the paper things, because in order to make the papers, there are so many trees which are being cut, which is also leading to the carbon emissions. And also there are some kind of hidden things there in administrative terms. It's like a loss to the exchequer. It's not the actual money which is being lost, but if this could have done in this way, this much would have been the profit. But now since this is not being done in that way, so this is kind of like a potential loss type of a thing. So there is both the electronic trail and the paper trails, but if you can restrict to the electronic thing, that would be a good thing. Would you like to add, Dr. Vinay?
Yeah, I'd just like to make a few quick points. Uh, First, I completely agree with that you don't need both. But here is the thing, in terms of practical steps, this is what was asked. You know, one of the things that we have to realize is all environmental problems related to unsustainability, which cause unsustainability in our interactions with the environment, are a problem of scale. It's really like if one person goes and takes a bath in a, you know, pond, no matter how dirty that person is, there are natural cleansing mechanisms in the air, the soil, the water that can handle that and regenerate, restore that ecosystem to what the natural baseline is. Okay, but uh, if 100,000 people go and do the same activity at the in that pond, then probably it will overwhelm the natural. So when we talk about sustainability, therefore, the one of the key checklists is to ask ourselves, is it something that will overwhelm the natural thing? And now, not every individual will have the knowledge and the depth to do this. So on very practical, everyday, sort of behavior, really a lifestyle change is required. What Brother Vishal was dealing on desires, which is that there is enough for everybody's need, but not for everybody's greed. So we have to arrest that. Now, how can we do that as individuals? I've seen this happen in Europe very, very effectively. and people are very patriotic and proud about it. One example, when you go to the supermarket, I remember looking at these guavas from Thailand, because you don't find them in Europe, and then going for it, and then immediately my colleagues are saying, "What are you doing? Do you realize what the environmental footprint of that?" I said, "What do you mean? These are the best guavas." We all want, and then they said, "No, look, calculate the cost of the transport from Thailand to Europe, the storage." So Germans, most Germans I met were very environmentally conscious in consuming only what is available locally and seasonally. That's one very big step. We sometimes have this tendency looking at these Hollywood movies or Bollywood movies, I don't know, that some big one thing will change the thing. But if you look at real life, it's the everyday things that have a much greater impact on changing the world than one big disruptor, so to say, no matter how powerful that is. So here's another thing that club can do. For every activity we plan at an institute level, there is a water footprint calculator. There is a carbon footprint calculator, which has already been mentioned when you undertake travel. So we can share knowledge about all of these different things. Then there is also very practical steps of how to recycle, reduce, all that we've been taught in school. And so essentially, if we could have a checklist, like I remember Swami used to say, if you have to do something, take a decision on something, then ask yourself first before plunging into it, is it good or is it bad? So if we could, before when we embark on these things that are likely to have a very strong impact in terms of consumption of resources, change a lot of things, ask ourselves, is it sustainable or unsustainable? How can I make it more sustainable, as has been mentioned along different themes? And then use these quantitative environmental footprint calculations for water, for carbon, for all the other things, recycling, yes, food, transportation. Then I think we would be changing our lifestyle to be more aligned with what is needed for the planet. So this, I think, is just, I thought I say that because I didn't want our sister to think something, one single thing would be enough to do the change. Any other quick questions? Otherwise, we'll have to probably end the session. Yeah.
I have two simple questions, sir. One is, in India, how seriously the policy makers have their ears for the, like yesterday you were presenting the air pollution statistics of Delhi. So as scientists, if you want to present it to the policymaker, is there a forum, and how seriously they take it in terms of implementation? What are the challenges they present to you? Because even after you give a very straightforward presentation, why is it taking so much time for implementation? That's the first question. Second question is, if there is a theft, we go to a police station. But if you see people dumping garbage on the river, or like we have this vehicular check, pollution check and all that, we do it for our scooter, and when we are driving, one bus will come, APSRTC bus will come, and then suddenly from white dress it will become black. So where do you go? You can't go to the police station. So many of us are just in the confines of our labs, we are trying what best we can do. But this is also on behalf of the students, when they see the society or the place where they're living, if these things are blatantly violated, it literally kills the spirit which they are. So how do you sustain in such circumstances?
Great. I'll try to answer it as best I can. Swami's inspiration. See, the thing is, many of these issues are like, we have to understand, if we really care about it, because we have only one planet, we will at some level have to take ownership of it. Now, taking ownership can go in different ways. You don't have to be the one who sort of marches to the district magistrate's office or goes to the police station. But just talking to your community, building the awareness, having a critical mass. There are social studies that have shown that you actually don't need a majority to make a meaningful intervention. Used to think that, okay, you write your paper and in your introduction, you've already written, this is why it's important, this is what should be done in the conclusion and the summary. And so why don't people just, take it? We've done our job. But that is a very pompous way of thinking. Everybody has their own priorities that they have to deal with, which comes with the nature of their job. Our priority is doing our research and writing our papers, right? So I can tell you this much: when I shared these same concerns which you mentioned, also for the benefit of the students, to the secretaries who advise the government on what the national missions should be and so on, and who are, by the way, scientists. In India, it may interest you to know that there are 3 ministries for which the secretaries are not IAS officers. They are actually scientists of great, distinction and repute and experience. So what he told me is, Vinayak, actually, if you tell a politician, whosoever it may be, doesn't matter which religious party, that this will be good for the people, they are willing to listen and they are willing to enable it to happen. What they don't like is one-upmanship or showmanship, where you go and you create a situation for them where they are defensive, where they turn out like it will reflect on them badly as a matter of incompetence, a lack of leadership in doing the right thing for society. No. So if you approach them, the approach is very important, I realize, in our system, in the right way. And the right way is, we are a functional democracy. So at your local village level, you have the sarpanches, you have at the district level, then you have at the MLAs, state legislative assembly, you have the member of parliaments. And so now in many places where the education level, all this is related to awareness in society, right? If most of the people are fending for the basic necessities, they don't have the bandwidth to really devote time and energy for this. But people who are already have a certain roti kapda makan standard, like in big cities of India, now they realize how bad the pollution is for their children, for themselves, for their parents. So then they have started making these awareness things. So that, I think, is the first step that we all can do. And coming to this, there are many technologies like this. If you look, even in India, we are sort of evolving with the times. The speed cameras, right? Speeding used to be a very big problem. But now with the automatic challan coming to the home, in many cities at least, that has worked to a large extent. Then you can have these guns where these are basically spectrometers, where actually they show you videos I can share with the students later, where they are positioned by the pollution control boards, and at least I know in abroad, some countries they do that, and at vantage points. And if there is a vehicle that's emitting dirty smoke, it actually takes with a laser the picture and the trace gas profile. So even if the cars has gotten a compliance certificate, which, as you said, they immediately get challaned, and then there's actually an investigation. So these are the ways in which we have to, technology has to keep up with, malpractice. So in short, environmental problems are wicked problems. As in, there is no one solution that will be a win-win for all the stakeholders, right? Like if we tell the industry, which, by the way, provides a lot of livelihood for jobs, money, right, for people, for their necessities. If we tell them, you completely shift this, then that is something, even if there's a better industrial alternative technology, they are not going to be able to do that, because it's going to affect the livelihood of so many people, business of youth. So it's a wicked problem in terms of who's going to win, who's going to lose. And for sustainability, we have to take a long-term view with some nuanced approach for what are the interim goals. But we have to change our lifestyle. There is no way around it. Because if we don't, anyways, the planet is telling us we're going to be history. So that's the thing.
Yeah, very nicely put, Dr. Vinayak. So I'd like to give my inputs on this point which you had mentioned. So one approach is to kind of communicate, to convince the policymakers, the politicians, to kind of take some action. It's a more of a top-down type of an approach. In some countries, I'm working in Himachal Pradesh. So there are certain villages in Himachal. These are kind of really sustainable villages. Maybe because of the distance and the remote location, they have to adopt the sustainable practices, but they are very happy and sustainable. Many of the villages in the Lahul Spiti district of Himachal Pradesh, and also in the other districts, we have a faculty from Hamirpur as well. So she might even tell more about the different villages in the Hamirpur. So there are villages which are kind of located. They adopt complete sustainable practices, wherein they grow their own food, whether it's rice or wheat or the seasonal crops. They grow their own fruits, everything, and they import very less from elsewhere. and also whatever is the waste which is being generated, like the cow dung, and those are being used as manure for the fields, and it's really a circular economy. They hardly have anything which is left to be thrown out to the outside world, and within, it's a small village, and village there in Himachal, just some 4 or 5 households, it's a village. A village can have even like 50 to 60 people is the population of the village. And before IIT Mandi took over the Command Valley, the Command used to be a very small village with 109 inhabitants. Still, there is a board which says that Command the 109 inhabitants. It's such a small village, but they adopt a lot of sustainable practices. A similar thing as an institution, since we are talking about sustainability in academia, as an institution, we could practice some sustainable practices within the SSSIHL Institute of Higher Learning, or like IIT Mandi or IISER Mohali or IIT Bombay, which is already following something. So let us be the change what we would like to see and bring in the things, and we should become a role model or an example which the politicians or the other villages or the other things could see and emulate the strategies for their things as well. It's just an input from my side. Thank you.
I think we're at the end of the time now. So we'll close the session here. We thank Bhagwan and all of you for the very nice discussions. I think the take-home message here is be the change you want to be, and practice is more important than preaching for all of us. Thank you. Sai Ram.
Sairam, thank you all for thank you all our distinguished panelists for your insightful contributions today. Your expertise and thoughtful perspectives on implementing sustainable practices in academia and in everyday life has been invaluable. The strategies and ideas you have shared will undoubtedly inspire further dialogue and action within our community. We deeply appreciate your time, effort, and commitment to advancing sustainability in academic environment. I would like to humbly inform the distinguished panelists that Sri Sathya Sai Institute of Higher Learning has a Center for Sustainable Development and also a green cell with faculty members from all the departments and students as members of this green cell. With Bhagwan's blessings and guidance, this cell is consciously moving forward with a motto to make the institute an exemplary institute in terms of sustainability. Thank you, sir. Thank you, sir, for offering your support and guidance, which we feel that would surely be very enlightening to all of us moving forward. May I now request our senior professor, Professor Sundareshan sir, to hand over a small token of our appreciation to the distinguished panelists. Thank you, sir. Now we have Dr. of used tools is such a fascinating idea in cost saving. Thank you, sir. Sairam. The second talk of today's session is by Professor Chandramouli Subramaniam. Sir is going to address us on the topic Sun and Sustainability, Materials for Solar Thermal Conversion. I request our student, Ms. B. Sai Mallika, to come on to the dais and introduce the speaker. Thank you.
Om Shri Sai Ram. It is my honor to introduce the speaker for this session, Professor C. Subramaniam, a professor at the Department of Chemistry, Indian Institute of Technology, Bombay. Professor Subramaniam completed his Bachelor of Science from Loyola College, Chennai in 2001, followed by an integrated MSc and PhD from the Indian Institute of Technology, Madras, where his doctoral research focused on the electrical transport properties and vibrational signatures of one-dimensional materials such as carbon nanotubes. His postdoctoral work at the National Institute of Advanced Industrial Science and Technology, Energy Materials. Sir's current work explores photon-phonon energy conversion pathways, aiming to create innovative materials for solar thermal conversion, electrochemical energy storage systems, and sensors for wearable electronics. His research also emphasizes developing novel techniques for understanding the complex electrified interfaces that are central to energy conversion, harvesting, and storage. A recipient of numerous prestigious awards, including the Young Scientist Award, Gold Medal from the International Union of Material Research Societies, the IJIMA Award, and medal from the Fullerene Nanotubes Graphene Research Society of Japan. He was also awarded with the Excellence in Teaching Award and the Impactful Research Award from IIT Bombay. Professor Subramaniam's contribution to science are widely recognized. He has published over 75 peer-reviewed publications and holds 10 patents, both Indian and international. In addition to his academic and research pursuits, Sir is also the founder of a startup dedicated to coatings for solar thermal conversion technologies. He has also served as a board member for ACS Sustainable Chemistry Engineering and as associate editor of the Bulletin of Materials Science. Today we have the privilege to have him talk about his groundbreaking work. So please join me in welcoming Professor C. Subramaniam to the stage.
just rearrange in my PowerPoint. Sorry for that. And I should also mention that if the as and when the PowerPoint comes up, I have taken the liberty to make a small change in the title of the presentation. I have just included Swami in the picture because I think without him, like I'll try to show you or justify the reason why I put Swami in the title of the presentation. Because I think without him, none of this was possible. And in fact, he was trying to kind of lead me into it. We are just tools in his hand. So wonderful. Thanks a lot for having me here. Thanks to all the organizers, particularly the chair of chemistry department and Sundareshan sir for having me at Prasanthi Nilayam. And so what I'll try to do is over the next 40 minutes or so, kind of detail some of the research activities that we are trying to do, particularly in the area of sustainability, because that is the theme of the conference. Yes. So the whole world is worried about warming. We are getting hotter and hotter. Everything is getting hotter. We can see distinct climate changes that is happening around us. Floods in Chennai was. I grew up in Chennai for best part of my life. 27 years that I have stayed there. I've never experienced flood. Probably tsunami once, but never flood. But now you hear floods happening almost every year, in that too in Chennai. So, and I'm sure that this is actually following a global trend, that there is whole global weather pattern is undergoing drastic changes. And so if you look at it, basically as this image shows, that's most of it is related to the global warming, that is the global temperature change, which is basically has a very strong correlation to the CO2 emissions. So as you, with time, year by year, if you see that the CO2 emission is constantly increasing, and simultaneously, if you look at the global temperature map or the weather map, that is also you see that is also having a continuous increase in temperature. And we are now at a threshold where global warming and climate change has become so very important that we are beginning to question our own existence because of various factors associated with it. So what I wanted to highlight was there is a very strong correlation between global warming and CO2 emissions that is already very well established through again data-based proofs and evidences. And if I go to the next slide, can you just move to the next slide? Yes. So now, because the next thing that is obviously happening, because if you want to arrest global warming or if you want to save our environment, we need to think about CO2 emissions. How do we tackle CO2 emissions? So again, like Swami says, prevention is better than cure. There is both a potential cure that is available, or at this stage what we can think of is can be thought of a prevention strategy also, and that is what I'll try to highlight. So when you think of cure, you continue to do existing policies, existing whatever damage you are doing to the environment in terms of industrial emissions, vehicular emissions, and so on and so forth. You continue to do that, continue to dump CO2 into the atmosphere, but then try to capture the CO2 and convert it or utilize it or store it. So that is one possibility, which is very popularly known as CCUS. So that is one way to do it, and people are very actively, including my friend Venkat, who was speaking about it yesterday, was potentially talking about how to mitigate or how to remove CO2 from the atmosphere and convert it into value-added chemicals. But while this is happening, you also need to look at CO2 reduction, not in a chemical sense reduction, but reducing the total amount of CO2 that we are putting into the atmosphere. And when we try to look at that, we need to understand why is CO2 coming into the first place. in the atmosphere. What are the major processes that are putting CO2 into the atmosphere? There, when we looked into it, we saw a very close correlation between thermal energy production and global CO2 emissions. It all started with the Industrial Revolution, that 1950s, 60s, 70s, when we started using coal or fossil fuels as a form of energy, as a form of fuel to do mechanized work for us. It can to run machines, and that is how Industrial Revolution started. So you see right from 1970, the black curve here, which shows how much thermal energy we are producing at a global level. It started from about 5,000 terawatt hour, and right now we are close to about 20,000 terawatt hour. That is the amount of energy that we are producing every year in terms of purely thermal energy. And when you see that, correspondingly the CO2 emissions have also started to increase from a very safe or a sub threshold level of 6 ppm. We are almost 6 times higher at 36 ppm of 36 gigatons of CO2. So we started at 6 gigatons when there was not much of industrialization and fossil fuel usage. Right now we have multiplied it by 6 times. 36 gigaton of CO2 is what we put into the atmosphere every year, and that this kind of a mapping gives us a very straightforward correlation between that. If you want to produce thermal energy, we invariably have to spend CO2, or we invariably have to exhaust CO2 into the atmosphere. So then we said that, next slide please. Yes, so why is that? Why is that correlation between thermal energy and CO2? If you see, if you can go back. Yes, so you burn anything that you can get. You start burning everything starting from wood. If you want to produce thermal energy, what is the immediate thing? You can think of any kind of chemical fuel. You combust it in the presence of oxygen. You will get heat out of it. At the same time, you will get CO2 as a byproduct, or an unwanted, undesired product. So now you take anything from wood, coal, petrol, diesel, kerosene, anything and everything, you burn it, you combust it, go through this chemical combustion, you will end up with a lot of thermal energy, but again, lot of CO2 emissions. And thermal energy is, I'm not saying that thermal energy is not important. Thermal energy is one of the most important and the single largest end-use form of energy that we are using. So thermal energy is, for example, used to generate electricity. All our nuclear power plants, thermal power plants, everything uses thermal energy to produce electricity. You need it for keeping your room hot, cooking, water. So these are some of the topics that I'll be trying to touch during the course of my presentation. So now, when we look at this kind of a cycle, that you need thermal energy on one hand, but at the same time you need clean thermal energy without CO2 emissions. But what is to be done is, if you see 45% of the global CO2 emissions, the 36 gigaton of CO2 that we are putting every year into the atmosphere, 45% of it actually comes from just heating two things, which is ubiquitous and which is extremely essential for our survival: air and water. We need air, we need clean air, we need sometimes we need hot air or warm air, and water, of course. So when you want to treat or heat air and water, you are unconsciously or without even our knowledge, we are putting in 45%, we are contributing to almost 45% of global CO2 emissions. So the question here is, how do we convert this red heat into green heat? Green heat is something which is without or devoid or minimal CO2 emissions. So when we make the entire process of generating this thermal energy green, then we can actually lower the CO2 footprint, and then try to think of sustainability. Next slide please. So then the answer, one of the answers to this, or what we our group at IIT Bombay strongly believes in, is in utilizing the power of sun. The sun provides us at least for a country like India, on an average, we get about 6.5 kilowatt hour per meter square every day. This is huge amount of energy. Believe me, on a global level, there are statistics which says that the sunlight energy, if we were to harness only the solar power, we will, the solar power that is incident on the earth, at half of the earth's surface at any given point of time, is basically 7,000 times higher than what we can ever consume. So there is a huge amount of energy that is available in our with our sun. And that we know, if you go into a little bit of details, the sunlight that is incident on us or that is available to us on the earth's surface is starting from ultraviolet all the way to the infrared region. Spectrally, you can say that you start from somewhere around 250 nanometers, you can go up to all the way up to 2500 nanometers. Of course, the spectral distribution varies whether you are in Chennai or whether you are in equator or tropical or Arctic or Antarctic regions. The spectral distribution varies, but the spectrum is more or less the same, 250 nanometers to all the way to 2500 nanometers. But the thing is that, next, I have a lot of animation, so you will have to just keep clicking, okay, whenever I say next. So when we want to harness this energy or use this, take this energy, soak up this energy, the most popular form of utilizing this energy is solar panels, photovoltaics, and photo-driven chemistry or processes. But both these photo-driven process and the photovoltaic panels utilize only the small part of the visible and some part of the ultraviolet region. Rest of the energy is just gone as waste. We don't even utilize it. So it's roughly 50% of the energy that is available in the infrared and is majorly lost. So we are doing a great disservice to the sunlight, which is showing us throwing from the spectrum from 250 nanometers to 2500 nanometers, while at the receiving end we are saying no, we prefer to work only with the ultraviolet and a small, maybe small part of the visible light. We don't want rest of it. That is a very great disservice. So next please. So the infrared component, which is largely ignored, is something which we wanted to concentrate more on, or rather we wanted to be impartial and say that let us look at the entire sunlight all the way from 250 to 2500 nanometers. And that's the question we ask: can we capture and utilize the entire range of solar spectrum? So now that yeah, next slide please. We are not the only ones who's doing this. There are a lot of other materials. In fact, Vishal brother made my work simple. He talked about black coatings and super black coatings. Basically, a lot of such coatings are available and a lot of materials are available. Some of the materials that are shown here are in the form of graphene, carbon nanotubes, or any other kind of carbons. Carbon becomes a natural choice because it is black in color. It's zero band gap material and a high density of states, means that it can absorb over an entire very broad range of sunlight or whole broadband spectrum. It can absorb very nicely. One of these, the best among these materials, if you look at the best among these classes of carbon materials, this is something called vertically aligned carbon nanotubes. So you can think of like you are walking through a very dense bamboo forest. So you have all these bamboos lined up very vertically, growing up very vertical. They are tall, and then what will happen is that the closer to the ground you will have very little of sunlight penetration, because all the light that is coming from the sun is actually absorbed by this structure of this material. That is exactly what happens. Next slide. Next. So no, go back. Yes, yeah, I can maybe operate this. Yeah. Okay. So so for a given photon which comes from the sun, irrespective of the wavelength, because you have this vertical bamboo structure like carbon nanotubes which are vertically aligned and kind of reinforce in each other, the photon energy is basically it hits one nanotube, part of it is absorbed, because first it is a black material, it will absorb. But then whatever is reflected or scattered from that nanotube will be absorbed by the adjacent nanotubes, because the bamboo structure is so very dense that once the reflection or the scattering from one bamboo is going to fall on the other bamboo, which in turn is going to get that is going to absorb. So that way you can increase the absorption of this entire film. So this is in fact holding right now the Guinness Book of World Records, the vertically aligned carbon nanotubes, which can absorb more than 98% of the solar spectrum. But the problem, one of the problems is that you have to have very flat surfaces. Such kind of structures cannot be made on a large scale if you want to think of practical applications. So, but we nevertheless had a very good inspiration from this. And next slide, please. Yes, and so there are other materials like again what Vishal brother pointed out, nitrides, titanium nitrides, chromium nitride kind of coatings, which are already in use in solar thermal coatings. So they absorb the sunlight. If you have a solar thermal water heater on the rooftop, these are the typical coating. Titanium and chromium nitrides are typically aluminum nitrides. All these materials are used to make these coatings which absorb. But then these are multi-layered structures. These are quite complex in to make. And the problem, as again, what was surprising to us was in India, we don't have any single entity manufacturing these coatings. Exclusively, every single solar thermal water heater tube that you get, 99.9% of them are actually imported from China. There is some technology resident with Hindustan Aeronauticals, but that's again not at a commercial level. They have not, as far as I know, they have not translated it to commercial levels. So what we wanted to do was get rid of all this complicated coating technologies, and we wanted to develop a single solar absorber which can single layer or coating of a single material which can do the exact same job, and carbon was a natural choice for us. Yeah, please, next slide. So now if you look at the solar thermal coating, what you need is a broadband absorber. That means a material or a coating which can absorb over the entire range of sunlight, starting from 250 nanometers all the way to 2500 nanometers. That means when you talk about molar absorptivity, it should be ideally 1. But then its emissivity should also be very small, because as material emissivity increases, it actually radiatively loses energy. So you don't want the energy to lose. So ideally you are searching for a very sweet spot where you have a large absorption but a low emissivity. And so that means emissivity should ideally be 0. And of course, it should be chemically and thermally stable. Processing, scaling, cost, all these things also gets into the picture. So now with all these criteria and parameters, and by understanding what we actually need from a material science perspective, we went ahead and started designing materials. So, and for this, we started from a very kind of a tangential object. We are looking for a black material. Remember, we are looking for an extremely blackest of the black material. But what we started was something which is completely white in color. Okay, that is what we started. These are porous silica structures. These are basically electron microscopy of these structures. It looks like this dandelion flower that you would see, exactly like that, but at the nanoscale, and is made up of completely SiO2. Now, SiO2 is very good because it is thermally stable. We can do a lot of processing with SiO2 without distorting the structure or without causing aggregation or collapse of the structure. So it's thermally very stable. But the problem is it is optically inactive. What do you do with the white material? You can't do anything related to light matter interactions with the white material. So we had to somehow make it black. Convert white to all the way go from one end of the spectrum, which is white, total a good reflector, to make it a good absorber. So how did we do it? We used this process again, thanks to Vishal brother, chemical vapor deposition of carbon on top of these structures. So we used a chemical vapor deposition process where you have acetylene as a carbon source. You thermally crack the acetylene, generate carbon species, and then use this silica, this high surface areas, what I call as dendritic fibrous nanosilica, as a template, and then deposit carbon on top of it. And then you can cover, because by varying the process parameters and the temperature and so on and so forth, flow rate and so on and so forth, you can actually cover all the pores of this structure, cover the entire surface of this structure with carbon. And then what you can do is you can use leverage the chemical instability of silica. Now, how is silica chemically unstable? Because SiO2 is sand, and you practically see sand right from even before human civilization was known. but then it's chemically very unstable. All you need to do is take silica and put it in mild acid or a mild basic aqueous solution, silica will dissolve. You can write a very standard textbook reaction, sodium hydroxide plus SiO2 gives sodium silicate, which is soluble in water. So you can actually etch out all the silica after you have made the carbon deposition, and you get something which is looking like a marigold flower. So this is a structure which is now, I started from here, came to here. This is now made up of entirely carbon, not a bit of silica is remaining. And because it's kind of looking like a marigold flower, we decided to call it as nanocarbon florets. And now we can go ahead and if you look at the electron microscopy also, there is a very clear correlation. What is exactly the structure of SiO2 which we started with is now completely now become carbon. The structure is completely retained, and it is important to retain the structure. I'll try to explain as we go along. And now we can make large scales of these structures. We can now make very uniform, if you see, very extremely uniform. Each sphere of this nanocarbon floret is exactly a replica of the you can pick out any two spheres and they are going to be very close and very similar to each other in appearance, okay, and also in properties. So now you can, and we also do the annular diffraction imaging, which says that all the silica that we started with is now completely removed. It is now a structure which is purely carbon and having this beautiful morphology like one of these marigold flowers that you see here. And we've done it scalable. Now what we need to understand more. It's just not enough to look at a good beautiful structure and say, it's beautiful. What is it really made up of? So we had to do a lot of characterization. I'll try to share some of the characterization techniques. First thing we did was, because it's a sphere at the nanoscale, we needed to not only understand what it looks like from outside, how does it look like from inside. So we kind of cracked it open, like much like how you do like coconut, you crack it open using harsh conditions, and then you can look at the cross section of this. So what appears as pores or the cavities on the surface is actually a cavity which radiates all the way to the center of the sphere. So if now what this electron microscopy tells us is, it's basically we have made a conical structure, and several of these cones are multiplied or copied and replicated in a 360-degree geometry. Then you will get a nice bouquet of these florets or these cones, and that is what this full structure is about. So you can think of it like a Japanese fan where you have a wide mouth at the top, and as it comes down, it narrows down into form of a cone. And you can connect all these cones in 360-degree isotropically. You will get a nice spherical at the nanoscale. Remember, we are all doing this at the nanoscale. So this is an open-ended pore structure with a high surface area, accessible surface area. So then we did powder XRD. Powder XRD gave us a very important clue for the structure of this material. So now we know that morphology, we know how is the morphology coming, because these are cones arranged. Now we need to go and look at the lamellae, the structure of the cone. What is that sheet composed of? So for that we did powder XRD, and we saw that by interpreting this XRD pattern along with evidences from electron microscopy, what we see is basically there are short range graphitic domains. So these are graphite like features which are arranged in the short range. It's a short range order, but then when you go to long range, this order doesn't persist. Say for example, if you take any form of carbon, this is fundamentally very important. You take diamond, even diamond, pure diamond, bulk diamond, you heat it to 2500 degrees centigrade, it will all collapse to the thermodynamically most stable form of graphite. Every single form of carbon will collapse to the thermodynamically most stable form of carbon, that is graphite. But here, because this is a short range order, the graphitic ordering is there only in the short range. The long range, the order collapses. That means if you start from one, you will see a few layers of graphitic like ordering, and then beyond that, that ordering will not be there. There will be another kind of a domain. So what we have created is this combination of short range ordered domain, which is graphitically ordered, and long range disordered domain. And now, because it is entropically so very high, the entropic penalty to make this structure is so very high, it will, irrespective of what temperature you take it up to, it will never convert to graphite. And this non-graphitizable form of carbon is what is called as hard carbon. It has nothing to do, the hardness what Vishal brother referred to was the mechanical hardness. It is carbon films made as hard films. Here, the structure of the material itself is called hard carbon. Again, nothing to do, it's a kind of a misleading term, because this hard doesn't refer to the mechanical hardness of the material. It is referring to the thermal stability of the material, its unwillingness, or it's impossible to convert this hard carbon into graphite, no matter what kind of temperatures you take it to or what kind of pressures you apply it to. So that is a structural stability of this material, and this is also extremely useful. And now, like I said, we can remove the silica. For forming the carbon, we remove the SiO2. So this removal can happen either in acidic medium or basic medium. If you do it with a base, during its natural process, that NCF, nanocarbon fluorides, gets somewhat functionalized with hydroxy groups, which makes it hydrophilic. If you do it with an acid such as hydrogen fluoride, HF, or buffered HF, you can end up with fluoride terminations which can make it hydrophobic. So you can play around with the surface properties or the surface chemistry of this material as well. And so, like I said, this is a disordered hard carbon framework which is non-graphitizable, which is very important in terms of chemical and thermal stability, and we have tunable surface chemistry. And this again, I'm kind of reinforcing the fact that this is a hard carbon, not only through PXRD or TEM. We have done extensive Raman analysis. I'll not go into the details, because the D band, which is again just for the sake of students here, the D band of carbon is typically called the defect-centered band. That's again a misnomer. The D in the D band actually refers to the diamond band. It was in fact Sir C.V. Raman measured one of the very first, maybe the top, it falls within the first 5 Raman spectra that Sir C.V. Raman measured. One of them was diamond, and he saw extremely sharp sp3, pure sp3 carbon. D band is a diamond centered band, which is used to identify diamonds. You can even now go to a jeweler shop, they will have a Raman spectrum to identify whether it's a diamond or a cubic zirconia or a piece of glass. Okay, so it's a diamond centered band, and this band actually is an indication of sp3 content, and we can do a lot of peak structure, peak fitting, and all those analysis on this to understand that this is the kind of structure, the hard carbon structure that we end up with, which is also supplemented by EXAFS and polarization microscopy and spectroscopy and so on and so forth. So we have something called the take-home message for this busy slide is basically you have a graphitic plane, and that is about 40 to 50 nanometers in size, the 40 to 50 nanometers in X and Y direction. It is stacked up to say 4 or 5 layers of it, which is the LC, 4 to 6 nanometers. That means you have 4 or 5 layers of this graphite arranged. Beyond that, you won't find the same arrangement. You will find a completely different arrangement. And if you go 5 nanometers further there, you will find a completely different arrangement. So that is the long range order breaking down, the symmetry breaking at the long range, but persistent at the short range. And and of course, you have a large accessible surface area. We can get about 1,200 meters square of surface area for every 1 gram of this material. It is electrically and thermally conductive, and we have also developed processes and dispersions. Because this is nanomaterial, you can't have a true solution, you will have a dispersion. We can now spray coat it on a lot of different substrates. Of course, a bit of surface treatment is involved. I'll not go into the details of that process. You can basically coat it into copper sheet. You can coat it on filter paper or PDMS, which is a viscoelastic rubbery kind of a material. So just to give you 3 examples, we can coat it on a lot more substrates. Just to give you 3 examples, because the surface energies of these 3 substrates are extremely different. You take copper, which is having a native copper oxide, it is hydrophilic. Filter paper, which is very hydrophilic. PDMS is extremely hydrophobic, it will repel water. So you can play around with the surface energies of the substrates and the dispersion solvents of the coatings to get very uniform coatings. And now the first thing that you see from all these coatings is that it is black in color, which is what we wanted. We wanted a black material to start with. So and of course, just saying it is black is not enough. We run a spectroscopic analysis. Basically, what we do is here we look at the reflectance. So you put light on a coating of this material, see how much of light is reflected back. And you do it from all the way from 300 nanometers to 2400 nanometers, which is very similar to the solar spectrum. What you see is after coating, before coating, if you do it on a, say, filter paper or any white substrate, you will get 100%, near 100% reflectivity, because it bounces off everything that you throw at it, irrespective of the wavelength. Here, after the coating on the same substrate, you see that the reflectance has come down extremely low. Similarly, you can also say how much is transmitted through it. So if you have a coating, how much of light is going through the material? Again, it is very low, if you see the red slide, red trace. And diffuse reflectance, which tells you how much is scattered from the material. How much of light, when you put light of a given frequency and intensity, how much is scattered from it. So you do all these three measurements to understand that it neither reflects light, the coating, after you apply the nanocarbon fluoride coating on a substrate, it neither reflects light, nor allows it to transmit, and nor scatters it. So then what happens is basically it absorbs the light. And how does the structure allow you to absorb it? If you see, like I said, it is having cones. So if you have electromagnetic radiation, say for in this case it is photons of a given energy and a given wavelength. So you have photons irrespective of the direction in which the photon is incident. Because it is a conical structure, it is going to undergo multiple internal reflections. Once it enters the cone, it is always going to go inside the cone and not outside. Because Snell's laws of reflection or refraction, whatever you want to take, optics allows you to optics allows the photons only to get internally reflected, not get out of the structure. So that multiple internal reflection, which is basically, you can think of a cone being a unit cell kind of a thing for the entire fluoride. You can put it in a photon in any direction and it is going to undergo multiple internal reflection, and that increases its absorptivity. It helps it to absorb more of the energy from the incoming photon. And so this is basically a morphological advantage that we have. Remember, I talked about the vertically aligned nanotubes, the bamboo forest to start with. We have replicated or taken inspiration from that structure and replicated it now that it is not a vertically aligned, but it's a conical structure, which does more or less the same job, that it allows the greater absorption of the photon energy from it. And now, we can now make all kinds of variations. We can change dimensions, we can change specific area, specific surface area, pore volume, surface chemistry, and so on and so forth. So each of these structures is going to give us a lot of different applications and a lot of different fundamental possibilities. But now for the time being, I'll try to restrict all the applications that I'm showing is with this kind of a nanocarbon fluorides. And so what we do is, now we know that it absorbs light energy. What does it do with the energy? Any system which absorbs energy has to do something with it. Either if it's a molecular system, you can talk about transitions, you can talk about spectroscopy, but this is not truly a molecular system, it is a material. Okay, it's a condensed matter. So now the simplest thing what we did was, like I said, we coated it on filter paper, put it under sunlight. Of course, we can do it in the lab and under controlled conditions, which we call as a solar simulator. And then you look at it through an infrared camera. Infrared camera, again, by the way, was very famous during the COVID time scales. And so you can you look at this, and then this allows you to measure the surface temperature of the coating. What we do, it's a very simple experiment. You take a filter paper, coat it, put it under sunlight, and then start looking at the surface temperature that it generates. So what we were in for a very good surprise, that when you look at it in the dark, this is a thermal image. You look at it in dark, it is as is expected, it is close to room temperature. But the minute you put it under sunlight, the temperature shoots up of the surface. The coated surface, the temperature shoots up and reaches almost 150 to 170 degrees. This is just pure green heat that we are developing on the surface using only sunlight. No other source, no electricity, nothing. And therefore no CO2 footprint associated with it. It is free energy coming from the sun, directly converted to green heat through this coating. And so the minute we crossed 100 degrees, the first question we asked was, can we evaporate water with it? Because water evaporates at 100 degrees, so can we evaporate water with it? So we made a very kind of a jugaad setup, Indian jugaad. So we cut the filter paper, made it into a kind of a stand. So now what we have is a reservoir of water in a beaker. Water rises along the filter paper due to capillary action. It wets the surface of the filter paper. At this junction, what you all you need to do is, because the material is already available on the surface, you need to put light. The light comes in from top. So what we have done is a tri-junction where light energy comes from the top, water comes from below, and both of this intersect at exactly the place where the material is. Material absorbs the light energy, converts it to heat, delivers it to water, and then you can start getting water vapor out of it. You can evaporate water. This is a real-time photo which shows that water is actually evaporating from the surface. So, and because we are now talking about energy conversion, we are talking about conversion of light energy to heat energy. What is the efficiency of this conversion? Like already I told you that there are solar panel coatings available, or for solar thermal coatings available, which operate at around 60-65% efficiency, ones which are available in the market. We can also calculate, because we know exactly the temperatures and all those things, we can exactly do the calculation. So basically P light is the total light that we are putting into it, alpha C optical Q, and environmental loss is basically radiative loss and convective loss. You can estimate each one of these parameters and arrive at an efficiency which says that if I put in 100 joules of light energy, how many joules of heat energy equivalent will I get? The answer turns out to be that we are getting close to 90% of conversion. So 90% of the light energy that we are putting on this coating gets converted to heat. And this efficiency is one of the, we believe is one of the highest in the field. Like I said, most of the commercial coatings, existing coatings, works at 50 to 65% efficiency, whereas this NCF coating delivers 90% efficiency. Here again, I had a movie. I don't think I'll be able to play the movie. No? Okay. So this is basically a movie where you see this, take this laser pointer and kind of, you don't need sunlight always. You can use very stray light sources like a very small laser pointer. This laser power, when you put it on the coating, is basically going to give you a 3 to 5 degree differential in temperature. Fortunately, I can't play the movie here, but we can, I can show it to you if you are interested. It is there in my in my laptop. So, and we can also compare it with other forms of carbons like graphene, activated carbon, multi, single wall nanotubes. We get the best or the highest temperature on the surface, mainly because our conversion efficiency is very high, and what we believe is happening is basically some kind of, we are confining the phonons or confining the heat within the material. We are not allowing it to dissipate. The radiative loss is very less, and therefore we can get much higher conversion efficiency and temperatures. So now how much of this coating is required? This is again important because we need to understand from when we want to go to scales, when we want to operate at scales, we can't, although it's a nanomaterial, we can't make it in tons of scale and try to use tons of material for preparing the coating. So we decided to optimize it. You see that there is a very beautiful sweet spot here, which is basically evaporation rate of water as a function of loading. How much surface loading are we going covering? And you see that anywhere between, I'm not going, will not go detail into the data. All we need is about 1 milligram, roughly on an average, 1 milligram of material to coat 1 centimeter square of area. That is all is enough. And we can, that means our scalability issue is also, we don't need to make tons of this material. Even if you make kilograms of this material, it is going to be enough to coat extensively large areas and make it functional. And again, I'll skip this data, this thing. So here, this is our benchmarking. So if you see the solar thermal conversion efficiency, we are here close to 90% with what many reports or materials have achieved with 2 sun or 3 sun, we are able to achieve with just 1 sun, which means that it's 1000 watts per meter square, which is the sunlight available on the Earth's surface. We can do it with that, and we have made a small prototype going from a beaker. We can now coat a terracotta clay, to coat the inside and just balance it by buoyancy on a bucket of water. You put the bucket in the morning in sunlight, and you come back, you will see in the evening some amount of water that is evaporated, and that evaporated water is about 5 liters per meter square per hour. So that means 1 meter square area of the material in 1 hour can evaporate 5 liters of water. And so we can also establish stability of this material. Now we know that this material is stable for almost at least 5 years of lifetime. And yeah, so this is the important point that I wanted to again talk in in the interest of students. Why is this material delivering such high temperatures? One of it, the fundamental reason is because, like I said, it's a combination of short range order and a long range disorder. When you put energy into a condensed matter, it starts, there are phonons that are getting activated. Phonons are nothing but lattice vibrations. So now, in a short range, nicely ordered kind of a crystalline, if you look only at the green area, it is a crystalline material. So the phonon activation is very good. It can absorb the energy immediately. Strong phonon modes get activated, and phonons are the heat carriers. The problem is, or the interest is, that this cannot propagate. If it were to be a perfectly crystalline material, it will propagate forever across the length of the material, across the dimension of the material. But here, in the short range order is broken because of the long range disorder. That means heat is somehow, you activate phonons, you generate the phonons, you produce heat in the material, but then the heat doesn't go out from the material, it is confined within the material. That means you are essentially removing or reducing the radiative loss from this material. And so emissivity is also close to 0.3, 0.4. It's very kind of a strange thing that for a material to have very high absorption and very low emissivity. So this is one of the few materials which satisfies this kind of requirements. And so this is basically, you thermalize and confine it by fractons. And so what do we do with this? Now, how much time do you have? Almost over 5 minutes? Yeah, sure. Okay, so what do we do with this? Again, all this is fine, provided what can be the uses, or what can we do with this material. So we did a very simple geometry. We took aluminum tubes, wound them in a helical form, and coated the inside of this with carbon. So you see before coating and after coating, this is a coating of nanocarbon fluorides. And now again, this is again a movie. Unfortunately, we will not be able to play it, but I'll be definitely there today and as well tomorrow. So if you want, if you're interested, you can come and I'll show you the movie. We have just assembled, put electronics and all those things. The idea is that oh great, it's playing suddenly. Okay, so you can just mute the, you allow it to play, but mute the thing. So what you put light on this coating, on this helical coating with the carbon nanotube, you flow in water. So now the point is, the heat that is generated by the carbon coating is now, because aluminum is a good thermal conductor, it transfers the heat, and whatever is flowing inside, in this case we flow water. So water which is flowing through the spiral gets heated up and comes out at around 85 degrees. So room water, we can take it all the way up to 85 degrees. Just without using any energy, meaning without using any CO2 related energy. All we are doing is using it in sunlight. So now if it reaches 85, the interesting thing is, one, you can get hot water, but the other thing of social importance is that 85 degrees, most of the bacteria and dangerous pathogens cannot survive. So it gets eliminated. So you can actually get contactless bactericidal action with a standard output of 40 liters of meter square per day. So, sorry, 50 liters. So you can get 50 liters of hot water at 85, which is basically disinfected against most of the active pathogens, thermally sensitive pathogens, and you can do it at with 1 meter square in a day. You can get about 50 liters. And how do we know that? Yeah, so we have actually done tests with E. coli. So you start from very high concentrations of E. coli, 10 power 6 CFU per ml, which is typically more than what you would expect in the regular water. It is close to kind of brackish water or sewage water levels, and you pass it through the device, within 10 minutes, your bacterial count reduces to almost zero. It's basically not detectable. No bacterial colonies start to grow. And we have also looked at 85 degrees. All these kind of pathogens are susceptible to the 85 degrees can kill, basically rupture the cellular wall. That means all these kind of bacteria and pathogens can be deactivated. And so now if you look at this for heating water and purifying it at 85 degrees, by heating to 85 degrees and purifying it, you can actually compute the total CO2 footprint of various other processes. Say for example, you use LPG, you use domestic stove, wood-based, coal-based, industrial boilers. All these has some CO2 footprint associated with it. Because we are doing using completely from sunlight, we are deriving all our energy from sunlight, our CO2 footprint by far is the lowest. And which means that even if 20% of 20 or 30% of Indian households start using this technology, you can actually save 20 million tons of residential CO2 per year. That's the CO2 savings that we can get, provided that this gets implemented even in 20% of, I'm not talking about the urban locality, I'm talking about real rural places where conventionally they do it with wood or coal or kerosene kind of stoves and things like that. So yeah, so this is one thing. Yeah, again, so now having done this water heating, we wanted to go one step further. And again, because it's a sustainability conference, United Nations Sustainable Development Goals, 7 of these goals are actually related to food, energy, water nexus. So what can we do? Basically, how much energy is required to purify water and how much clean water is required to generate energy? That's the question. So what we said we will do is, I'll quickly, I don't have time to go through this. We designed a setup which basically, now if heating water to 85 degrees is one thing, but then if we can heat that water to 85, we can also take it little above, we can basically increase its vapor pressure, condense the water, and water vapor is basically the purest form of water. So if you condense back it, you will get the most cleanest form of water, irrespective of what water you started with. It could be saline water, it could be brackish water, it could be any kind of water. You evaporate, only the water evaporates, and you condense it, you always end up with clean water. So we designed a setup based on this. So we basically combined the material with a systems level design. I'll not go too much. So this is actually the setup. So you have the heat generating surface. You generate the heat on the top. Through a conductive fluid, a thermally conductive fluid, you transfer the heat to the water, and you evaporate the water in this chamber, which is the water evaporation chamber. You condense it using a lid, and water vapor is generated here and also condenses here, and then you collect the water at the bottom. So it's a vertical setup, 3 columns, 3 parts. Top is the solar thermal coating, which generates the heat. The heat is then transferred to water. Water evaporates, it's recondensed back, and then you get pure water at the bottom. So now with this, we have actually done tests in at IIT and also in lab scale. We have implemented tested with 10,000 ppm of saline water, just to kind of have salt content, see what happens if the water is saline. 10,000 ppm is almost twice that of groundwater TDS. And so the rate of conventional solar stills is about 5 to 6 kilograms or 5 to 6 liters, 7 liters of water for every meter square of the device area in one day. So conventional devices can give you 5 to 7 liters in one day, whereas our device, what we have implemented here, can get 3 to 5 liters of water for the same device area in 1 hour. So with 6 hours of usable sunshine, you can basically get about anywhere between 18 to 30 liters of pure water. Again, we are not talking about industrial scale ROs, small household level. If you just put this unit in the top of your house, put water, groundwater in here, you will, at the end of the day, you will get 30 liters of clean water, which a small family can handle. And this was actually tested in Kutch, Run of Kutch area. We have kind of implemented a larger scale plant in Run of Kutch area. I'm just showing them how to handle the device and all those things. So why Run of Kutch? Because that's where maximum amount of salt is being produced. There is a particular community in Rann of Kutch called Agariyas, about 1 lakh people who produce 99 or 97 to 99% of salt in India. Whatever salt, Tata, this, that, every kind of salt comes from these people. This 1 lakh people are the ones who harvest salt for 6 months of a year. And the problem is, because the salt is, it's basically a salt desert. So you will not have water there. You will have plenty of salt, plenty of brine, you will not have water to drink. So now you take the salt or the seawater and you pass it through the device. The idea is, can they get water at least for their drinking during the 6 months of the year? 30 liters per household is something which can be thought of if implemented. We've already put up a pilot plant. We are trying to implement it at a much larger scale through CSR. So again, like I said, the CO2 footprint, the device is called SunSpring. So because it's a spring for use in the sun. So, and we believe that we can reduce the carbon footprint, at the same time provide clean and affordable drinking water. Now, last 2 minutes I'll take, sorry. If we can heat water, heating air becomes all the more easier, because air is having much lower specific heat capacity than water. So you need much lower energy to raise the temperature of air compared to raising the temperature of water by the same amount. So all we did was, instead of flowing water through the tubes, we flow air through the tubes. And what happens? Air comes in at a much higher temperature. In fact, we can reach about 150 degrees centigrade with air. And now what is this used for? We went all the way to, I can't name the place, but it's an Indian Army locations at very close to our POK border, where you can see huge snow. We went there in May or December or January. In fact, the last trip we made was in February this year, earlier part of this year. It's completely covered with snow. But the paradox is, it's also beautifully beautiful amount of sunlight is there, because it's very clean. As you go to higher altitudes, remember 14,000 feet, volume of tent is about 5,000 liters. Oxygen level is very small, very low here, because as you go high, your oxygen content reduces. We can take the heat, light from the sun, convert it to heat, and then deliver it into these shelters, which typically becomes 5 or sub-zero temperatures. You can heat it up to 15 degrees, which is a very comfortable weather, living conditions for our Indian Army Jawans. Again, the closest technology that is there is they burn kerosene. Kerosene has two problems. Burning kerosene to get heat has two problems here, especially because, one, you are having a huge fire problem. Any small spark, all these shelters are made up with FRP, fiber reinforced plastic. So one spark of this fire can land, the shelter will combust in no time. Again, your oxygen content is already depleted. And for kerosene to burn, you need more oxygen. You are already sucking up oxygen from a depleted environment. So we have done this testing, and we have also compared it with other users, and that all these testing and field testing and this gave us the confidence that we can go ahead and incorporate a small company, which call it NCF Green Energy Private Limited. We have 3 plus few other members. So like I said, what we started looking at it as a 200, 300 milligram scale in the lab. We can now make it at this rate of 250 to 300 grams per day using a pilot plant under this company. And we also had this opportunity to present all these innovations. Here again, I had to mask these people's faces because they are related to they are kind of top brass in the army. So for confidential purposes, I had to mask it. We are kind of giving a demo or a, what is this called, a model unit of this, just handing it over to the Jawans, and already we are all in our thermal coats. And this is us presenting it to our Minister for Education and Defense Minister. We had all these nice opportunities for us, and now we can, it's also came up in news, and we can now, we are now doing a translation, or some of the units, like I said, is part of it is there in Rann of Kutch to give water at low energy cost, and some of the units are already delivered to the army, our army in northern altitudes. So we want to take this forward in that way. It's a startup that we have incorporated. So besides that, I also, one of this is solar thermal. So, but like I said, kind of work in other areas also. I would be interested in talking about all these things. This is my group, NCF Labs, collaborations especially. I love the collaboration with Parthi Satyasai Institute. It's a second home for me. And all these students, and Dr. Seemesh was there for some time after he finished PhD here. So that was a very fruitful time. And yes, coming back to why last slide from my point, why I had Swami in the picture, in the title is, he is the Veda Purusha. So he is the ultimate Veda Purusha, and this is him sitting on the Purnachandra chariot, the golden chariot, symbolizing the sun. And more importantly, Swami gave us always tells that Vedas is the epicenter of all our knowledge. All of mankind's knowledge is kind of nested in the Vedas. And that, I realized that that statement is so much true, and Swami has a huge role in whatever we have done so far. We have not done anything new, believe me. Even after this, it's absolutely millions of years old Vedas, which is already enshrined. We are just not been able to see it, because what do we say in our Surya Upanishad? If the slide comes up, yeah, Adityad Vayur Jayate, Adityad Bhumi Jayate, Adityad Apo Jayanti. It's from the sun comes the heat. That's already there. So I'm basically, we didn't do anything. There's one more. Yes, that's the highlighted portion. So we didn't do anything. It is all Swami's hands guiding us. We are mere we believe we are mere tools, and it's a Swami's way of leading us forward. So thank you so much. Yes, no problem. Sorry for taking up too much time, and I'll be available today and tomorrow. So anybody, I don't think there is time for questions. So, I'll certainly be available for further discussions. And if anybody wants to see the movies, also I'll be happy to show them. Thank you.
Thank you, sir. Anyone interested in interacting with sir, please contact sir outside the seminar hall. Thank you, sir, for such an enriching talk on Swami, sun, and sustainability, materials for solar thermal conversion. The solar absorber, a carbon-based material, nanocarbon florets, which is a conical structure with varying dimensions, specific surface areas, pore volume, is such an efficient solar thermal converter with about 90% efficiency. This innovative idea of using these converters in water purification without CO2 footprint is truly remarkable. Similarly, the setup of transferring heat through water and then recondensing it to pure water is awe-inspiring. Thank you, sir. May I now request our beloved Professor Rajni Bhandari ma'am, HOD, Department of Chemistry, to present our token of appreciation to Professor Chandramouli Subramanian. Thank you, ma'am. The next talk of this session is by Dr. Sampath Koppale, Products and Solutions Lead, Healthcare and Life Sciences, Google, Switzerland, on the topic, The Frontiers of AI Research. Sir is joining us through hybrid mode to deliver his talk. I request our student, Mr. Hari Krishna, to introduce Dr. Sampath to the audience. Thank you.
Om Shri Sai Ram. I offer my humble pranams at the Divine Lotus feet of Bhagwan. It's my great privilege to introduce one of the eminent guest speaker, Dr. Sampath Koppale. Dr. Sampath Koppale is an alumnus of our university, having completed his bachelor's in chemistry from the Brindavan campus and a master's in chemistry from the Prasanthi Nilayam campus. He then went on to do his MS in Chemical Engineering at the Indian Institute of Sciences, following which he did his PhD in Computational Biophysics at Heidelberg University, Germany. Dr. Sampath has accumulated extensive experiences across various roles, including his tenure as a global head for real-world data at Hoffmann La Roche AG, Switzerland, where he led initiatives to leverage real-world evidence in drug development. Prior to this, he served as an assistant vice president at Data and Analytics in Infosys Technologies, significantly improving analytics capabilities and operational efficiencies. Dr. Sampath is currently engaged as the lead at the Products and Solutions, Healthcare and Life Sciences, Google Switzerland, where he leads teams of solution architects and software engineers to execute AI and machine learning research projects in healthcare and life science across Google DeepMind and Google Cloud. With a robust background in data science, machine learning, and AI, he has made significant contributions to projects aimed at enhancing drug discovery and development process. His technical skills are comprehensive, covering areas such as advanced analytics, data modeling, and machine learning techniques. Dr. Sampath is a proficient in tools and technologies like Python, R programming, SQL, and various data visualization platforms, making him a versatile asset in any data-driven environment. Please join me in welcoming Dr. Sampath Kopale.
Sorry. Can you hear me well? I was on mute. I apologize. If somebody gives me a note that you can hear me, I can start.
Yes, sir. Yes.
Yes, perfect. I see somebody putting up a thumbs up there. Thank you very much for giving me an opportunity to present in this symposium. I start off offering my most humble pranams at Swami's Lotus feet. And what I'm going to present in the next few minutes is basically what kind of research we are doing across Google and how it impacts the different things. What is the background, and also about our progress into AlphaFold, which got the Nobel Prize this year. Can you see my screen? I'm just ensuring everything is fine.
Yes, sir. We can see the screen.
Yeah, I assume we can see the screen. Okay, so first and foremost, whenever we start and talk about AI, Google has taken this position that we need to build AI responsibly and to benefit humanity. What does that even mean? What does responsibly means? So AI, as somebody has described in ways, AI is very, very focused in specialized area. It is way better than any other human there is. But if you talk common sense, AI is not there. It's common sense lacks in AI. That's the general feeling people have. And so when we build AI, especially, we need to be very, very careful as to what it's going to do and how it's going to do and what impact it has on humanity. So we think about when we build AI models, AI tools, we need to have a full open dialogue with people around in the community to understand how it impacts different communities around us. That means it makes sure that it is unbiased, it helps humanity in general, and does not cause unnecessary trouble, because there are two parts to the problem. One is the AI tool itself, and the other is the humanity using these tools. So the tool itself may be agnostic as to the use, but humans using it need to be very careful as to how we use it and how it benefits humanity. So we need to put guardrails in terms of regulation and control of AI. At the same time, we need to develop AI so that it benefits humanity, it makes us more productive. So that is our overall view and overall goal in whatever we are doing at Google. So the next question is, whenever AI, artificial intelligence, why is it so important? Because there is a lot of intelligence among us, and we need to make sure that this intelligence is there to help us in terms of whatever activities we do, maybe making us help be more productive in terms of managing our calendars answering, writing emails, in every aspect of our life. This has dramatic impact on all parts of our being. So the way we look at it is, this is a picture of the industrial revolution that happened a couple of centuries back, where we used to produce products and materials for the village, for the community, and from there we started scaling up to produce materials and products for humanity. And that was a big step, going from a very minute scale of serving the community or a village to serving countries and the planet. So from there, now we are at the information revolution, where we have all the information we want on our fingertips. We can access almost everything. Most of the data that's there is available in the open world, open internet. We can access this. We can do all kinds of things with this. And now we have, with this, AI coming in, and AI could be one of the most important inventions in history. It is going to make us be way more productive. It is going to help us really accelerate in terms of what we can do and what we can achieve for the betterment of humanity. So that is the most important thing, that we need to focus on how we build these tools to the betterment of humanity. So how do we think about AI? So AI, the way the rest of the talk we have, AI needs to meet the root of a problem. So we have a root problem, and if we can really handle that root problem, then everything around or that sits on top of it gets solved, because we really went to the root of the problem. So AI is there at the root. So all the products that we are developing are really looking at the fundamental issue which we have in terms of how we can make humanity better, how we can help humanity. So before we started doing anything on building tools, we needed to make sure AI can meet the requirements of humans. So we thought the best and the safest way is to play games, because it is very safe. The worst case scenario is you would lose the game, and that's it. Nothing would happen. So we first, as DeepMind, we went and played this game called AlphaGo. What is AlphaGo? AlphaGo, there is a big grid of squares. Each of them, there's a black pebble and the white pebble, and you keep the pebble on this grid, and you need to conquer areas and so on and so forth. I don't want to go into the game itself, but what is so interesting about this game is the number of possibilities that are there is, for every position, is 1 to 10 to the power of 170. The number of atoms in the universe is 10 to the power of 80. So it's way more than the number of possibilities that are there. So it cannot be a game where a machine can just elucidate all the possibilities, take the best possibility forward and go, because to compute each computation, to compute the next possible, it takes longer than the time of the universe. So there is no machine that can do. So the game has to rely on intuition. So the game, AlphaGo itself, the Go game itself, is biased towards humans, because when I play chess, when I play Go, or I don't play, but an expert who plays Go, they have intuitions. They've played so much that they have a feeling in their gut. They know what is the next move they have to do, so they can do it. And a machine cannot do that. The machine just enumerates all the possibilities and goes through it and then defeats. So effectively, this game is already biased to humans and not towards the machines. So we thought, let's play this game. So what we did is we built up a program, a solution called reinforcement learning, where we let the game learn the game by watching all the games that are there. So it just watches, it doesn't do anything else, and it starts to capture patterns and see what these patterns can do. And based on that patterns, we build a neural network, and there's a model that is made available. And the model per se, based on the pattern that is there and the previous patterns that are there, it predicts what could be the next pattern and so on and so forth. And then it just works on the pattern. It does not enumerate everything, every possibility which is there, which is a completely fundamental way of looking differently from the previous systems, for example, IBM Watson and so on and so forth. So this is the new way to look at the system. So once we built it up, we called Lee Sedol. He's a world champion in AlphaGo in the game, and we called him for a $1 million challenge in Seoul 2016. There is a documentary of this on Netflix. You can have a look at it. It's a fantastic documentary where the game was played against Lee Sedol, and in the beginning, Lee talks about saying that, oh, we'll see a machine defeating a human at the game of Go is almost impossible, and he understands the challenge, etc. And he kind of talks about it, and then they play, and there were 200 million viewers, live viewers, and AlphaGo won 4:1. And it was really, really amazing. Means he couldn't believe. And in the middle of the game, he says he needs to take a break because he sees the system is playing way better than he is playing, and he takes a break, and you can see all the emotions that go through. And what is interesting is there is in one of the third game, there's a game move called 37, which all the experts in Go watching this saw that this is a move which nobody even envisioned. So the machine envisioned a move 37, which defeated Lee just out of it. Just it was such a fast game that the move 37 somehow in the placing of the pebble there defeated Lee very, very quickly. So what we did, we managed the complexity, 10 power 170 positions, and we won 4:1 and the famous 37 move. Everything was done through self-learning or reinforcement learning, where AlphaGo watches the different possibilities that are happening, looking at the patterns, the previous patterns, the current patterns, and predicting the next pattern, and so on and so forth. And we really good it. So what we have done is essentially we applied the machine learning tools to a game, which is the safest way to develop any kind of model. So now 2016 AlphaGo came out. AlphaZero was released in 2017. And in 2020, we released what is called MuZero. Right now, MuZero is you just show the machine a game. It figures out, and you don't have to give it any rules. You don't have to say anything about it. It just looks at the game and it figures out how to play and defeats you in the same game. So that is the level of expertise which we have reached in terms of gaming. So now that we have learned and we are very confident that we can build safe, or we can really build productive AI systems, we started applying it to Gemini. So Gemini is based on a paper which was published called the Transformer Model, Attention is All You Need, is a paper which was published in 2017. And Gemini was called BARD, and now rebranded to Gemini. And the recent 1.1, and now we just released a week back 2.0. So what I'm talking about is 1.5. So a version behind. So what we did in Gemini is we did multimodal. So we brought all the different modalities of data, that's images, text, sound, and video, all of them together, so you can interact with the system and ask questions, get inputs, get answers in a very, very multimodal way. So you can tell it to make videos, you can make it, I'll talk about different things which are going to happen about how we apply Gemini. And so this is what came out of this. And there are three models, Ultra, Pro, and Nano. Nano basically runs on the machine, on a device, and Ultra is the largest and the most complex Gemini model there is. And it takes what is called 2 million tokens. What does 2 million tokens mean? It basically means it gives context. So if I give it, see, this is a context, I want to go to Zurich. How do I want to go? Should I take a train, or should I take a bus, or should I fly? So the context is I need to travel somewhere, and that's a very, very small token. It's hardly a few tokens. But if I can increase the token, and in 10 million tokens, if I can give it a 1-hour video and tell it, please summarize this video. That's it. And it will summarize to you in, let's say, 1 minute. Or you give it audio of whatever length, 11 hours, and then it can summarize. It can give you in text. Tell me what happened at 10th hour and 16 seconds time. It can figure it out, and it can tell you what was happening, what was the context, and so on and so forth. And so it has a lot of context, and that is what we talk about, the tokens, the context tokens, which are available. So we have built this amazing ID technology, but now what is happening is there is the barrier between what humans produce and what the machine produced, the barrier or the line is slowly disappearing. So the first thing, especially going back to building safe systems, safe AI systems, we needed to make somehow have a kind of fingerprint to really decipher what is human produced and what is machine produced, and to really decipher and make sure that nobody can take out a machine produced content. We develop SynthID. So what we do watermarking. There's a small video here. I hope you can see it.
Is this real or AI generated? Sometimes it can be difficult to tell. For hundreds of years, humans have used watermarks to prove where content was created. One challenge is developing a mark that's hidden to viewers but visible to those looking for it. Enter SynthID by Google DeepMind. It can produce a digital watermark that's imperceptible to humans and works across Google products to tag AI-generated images, video, audio, and text. The watermark can withstand common editing techniques like reordering and trimming, adding noise, compression, cropping, and filters. How? For images, it can be embedded directly into the pixels. For video, it also marks every frame. For audio, SynthID converts the signal into a spectrogram, a visual representation of the sound waves, into which it embeds the watermark, before it converts everything back into a waveform. For text, SynthID looks at which words are going to be generated next, and changes the probability for suitable word choices that wouldn't affect the overall text's quality and utility. If a passage contains more instances of preferred word choices, SynthID will detect that it's watermarked. You can't read, hear, or see the watermarks, so you can fully enjoy your creations. SynthID technology is already used across generative AI Google consumer products. SynthID is just one tool we're using to make sure generative AI tools are built with safety in mind from the beginning, empowering people and organizations to create responsibly.
So so how does it work? So if you take a text, right? So if I write a sentence, my favorite tropical fruit are lychee, mango, papaya, or durian. So it produces two probabilities. One is what will be the probability of the next word plus some, that's the probability of the LLM and the probability of watermarks. And for every word, these watermarks get embedded as probabilities into the text, and then you can extract those numbers out, which is the text itself. The watermark is embedded in the text, so you cannot edit it. And exactly this, as long as this probabilities are there, you get access to, you know that this is generated from an AI machine. And you cannot get rid of it. The 99.9% of this email that was generated is with AI generated. So essentially everybody knows that this is AI generated content. Here is a movie, a song, and you can see that you cannot make any difference between what is original, what is watermarked. So I'll just go to the next one, and then these are the photos which are there. You know, you cannot make a difference between what is watermarked and what is, it's completely embedded into the whole thing. So what we have done is we built the systems, and we kind of built in safety measures to make sure really what is AI generated and what is human generated, so that human creativity is still appreciated and people know the effort a person has put in generating that content. The next thing, as we said, in the beginning, that we look fundamentally at root problems. So one of the biggest problems is understanding materials. The previous speaker spoke about the amount of effort that person went through to bring the specific materials which are very, very efficient in harnessing light, sunlight. So we are trying to use AI basically again to do what all the materials one can explore in terms of generating new kinds of materials, and that is what is GNOME or Genome, Graph Neural Network for Material Exploration. That is the acronym there. And so what we did is basically we built two pipelines here. So we went through the top pipeline where we knew crystal structures of different materials are available, and we generate similar structures which we already know. So these are crystals which are available, we generated. The other one at the bottom is essentially a random search approach. We try to go wild. We generate multiple structures in a more randomized form and with chemical form. So there will be a lot of errors here, but doesn't matter. But then we use a DFT, density functional theory. This a mathematical model where you evaluate materials based on orbitals and so on and so forth. And we generate a GNOME database, and then we generate new materials, because the lower pipeline generates so many new materials that we cannot even think about it. And then we have the database, and then when we look at the database, until now, until 2021 or 22, humans had, by experimental work, had generated around 50,000 materials. And in 22, when GNOME came in, we generated 400,000 materials. These are all stable materials, 421 materials here. And until recently, with computational methods and human interpretation, we had 20,000 were done by human interpretation and 48,000 were done with some kind of computational methods. We basically 10 times went up with number of materials that are available. We are building these materials which will tell you which have better electromechanical properties, especially for electronics and energy storage, especially from the previous speaker. What are those materials that we can utilize? That is what we are interested. And we published this genome database. It's publicly available. You can access it. And we have found new alkaline earth-like materials for optical properties, which have potential superconducting properties, which are huge amounts, where we could use it to store energy and harness it back. You can imagine these materials can be the energy can be stored from one of the Thar deserts maybe, and then that energy is stored and can be sent to all parts of the world, or to India, essentially in India. And we are kind of giving the recipes how to build these new materials. So what we did, we also went and collaborated with experimental research universities and experimental research labs and companies, where we built up, the machine would take the computations, it would send up using LLMs, right? Large language models. We will write a recipe, how you can create that material, and then you go through a whole process of phase identification, recipe optimization, and we go through a kind of a cycle and really generate all these new materials in reality. It's not just AI generated, it could be fiction, it may work, it may not work. So we tried most of these materials in a lab. So what came out? So with all the recipes we generated, we had 58 targets, we got 41 targets. So we could get really good success. And out of 355 recipes that were generated by LLMs, 130 recipes worked. So effectively, our outcome was basically, out of 355 experiments, 41 out of the 58 novel inorganic crystalline structures were available. The success rate is 71%, which is one of the best you can think about it. And this really accelerates in terms of producing new materials for different purposes, different parts of the industrial chain where we can produce. This technology came out in 22-23. So we are really closely following and supporting different labs and industries where we can really help and help them achieve their business goals. The next one is called GraphCast. So one of the most important thing is weather prediction. So right now, the weather prediction models, what they do, they use numerical methods, basically finite difference method. They have this huge variables which have long equations are written based on multiple factors, and these equations these are differential equations. These equations are solved, and then you predict the weather. And this is a whole system, and extremely computationally intensive. And what we have done is we said, okay, the weather is an important part, and we built a weather model where we, for every 25 degrees, or that is 28 kilometers by 28 kilometers at the equator, we generate the input weather, predict the next weather, and from the previous weather conditions, it takes the weather conditions and predicts the next weather, just like we did in AlphaGo, right? You have patterns. You can imagine of that kind of pattern. The patterns available before. What was the previous pattern, what the current pattern, and what will be the next pattern. It's like prediction, so it's way cheaper in terms of computation. And at each grid point, it takes 5 surface variable: temperature, wind speed, direction, mean sea level, pressure, etc. And then it predicts what will be the weather like. This is a small video again, which we...
For centuries, humans have struggled to understand the weather, from putting a wet finger to the wind, listening to cricket chirps, and looking to the stars for answers. Now we believe AI can help us advance and understand how we can predict it. Meet MetNet3 and GraphCast, our deep learning models designed to generate more accurate weather forecasts. Traditional methods work by simulating entire systems, with hundreds of variables interacting. In practice, this means abstracting those variables into equations and then manually coding them into algorithms. Our AI models take a different approach. They analyze past weather data to learn cause and effect relationships between weather conditions. These learnings allow the models to find subtle trends and patterns inside the data, which they extrapolate to predict what could be coming. MetNet3 and GraphCast outperform the best systems in the world, seeing further into the future more accurately, efficiently, faster, and in better details. For everyday and even extreme weather, is already improving the accuracy of 24-hour weather forecasts on Google search. And we have open sourced the GraphCast model, which the ECMWF is using to generate forecasts and make them accessible on their website. Imagine a future where we can help people to prepare earlier for hurricanes, enable farmers to grow better crops, or even help us decide if we should pack an umbrella. AI won't just help us predict the weather, it'll help people make better decisions about their lives.
So as you can see, going to the root problem, right, about predicting the weather, you can really see implications to farmers, implications to humanity. Again, looking at it in a broad sense, how AI can help humanity. The last topic which I want to talk about is AlphaFold. It got a Nobel Prize recently. I'm very fortunate to be very closely involved with AlphaFold and work with its development. So what is AlphaFold? AlphaFold is basically, if you give a sequence of amino acids of a protein, of a protein which comes out, it could be a target, it creates a 3-dimensional view of the protein. Why is it interesting? Because in human biology, the whole biology runs with proteins, and usually we need to understand the structure of this protein so that we can interact, we understand its function, and sometimes in a disease state, the protein is not functioning or functioning more, and then we can create small molecules which can bind to these proteins and modulates its function so that we can control its function. So it's very important how the protein looks like from the sequence. Here you have a jumbled letters. These are basically, there are 20 natural amino acids. There are 26 alphabets. So what the scientific world has done is, for every amino acid, they're assigned a letter. So there are 6 letters that do not have an assignment. That's B, J, O, U, X, Z. These are the 6 letters which do not have an assignment. Rest of all the amino acids have a letter assignment. So it's basically the sequence which is there. And we just input the sequence, and the machine, the AI model, predicts the structure of the protein. And this was a grand challenge. This was the 50-year-old challenge. I was very fortunate to work on this product, on predicting the protein structure during my time at Heidelberg, and also during my time at Novartis, to predict the structure of the protein, because that is one of the first steps when you want to create drug-like molecules, which can really help mankind. So we kind of worked and create this solution. And right now, it's an iterative step. It's a very detailed algorithm. I could go into it in a full 1-hour lecture, but essentially what we do is basically take the structure, we do feature engineering, understand what its sequence looks like, and then see what part of the protein is conserved across evolution, because evolution is a very interesting part. If a protein sequence is conserved across evolution, that is the way a hemoglobin
transfers oxygen from the lungs to the rest of the body, the way it works in a dog, in a pig, in an elephant, in a tuna fish, in humans, is essentially the same, but the sequence is different. And so if we can understand what part of the sequence is conserved because the functional part is there, and then you put attention on that and you build the attention-based model and you predict the structure. So it is a very, very interesting thing. And what we did is, again, in the context of humanity, we went out and every known protein to man, there are 214 million proteins. We created a database and put all of them in the EBI, European Bioinformatics Institute of EMBL, in London, in UK. And now it's freely accessible. So anybody and everybody across the world can just access these databases, these proteins. And if they're working on a particular protein, they can see the structure of the protein, understand what it's doing, create different molecules. You have a good start in your drug design journey. And we have given this, as I said, we have given this as a free knowledge to the world. And now as I speak, this AlphaFold technology is working, helping better crops. So especially in crops, you can think of for crop protection. That is, you need to create insecticides that kill the different insects that are biting into your crop so that your productivity is high. But at the same time, you don't want that those molecules or chemicals that are put don't hurt bees. They have to be very specific to say locusts or one of those insects that are harming your crop. So you can create specific products which against a specific insects and then only kill that and don't kill the rest of the ecosystem. So you have an eco-friendly productivity of your crop and so on and so forth. That is there. We have seen AlphaFold being used in plastic pollution. So we can create enzymes where they just eat up the plastic which is in the oceans and so on and so forth. So there are so many applications which you have done. One important thing is neglected diseases like tuberculosis, cholera, malaria. These are diseases from the tropical world, because we can really go in and see how the particular pathway, the physiological pathway of a particular bacteria is there, and really hit it there, and only that. And so you don't do unnecessary harm to the human, and so on and so forth. So there's so many other applications of AlphaFold is coming out, and everything of this available freely for mankind. We also developed what is called Alpha Missions. I will not go into it, where what we have done is we have basically gone and looked at the whole human genome, and we kind of look at the genes and say which particular gene mutation is pathogenic for the human and which gene is not pathogenic, or is it is docile. It doesn't have no impact on the human health, and you can really go and look at the genome and find out. So we have combined AlphaFold with genomics to really go and look at. So all we do is we take a genome sequence, we look for pathogenicity in the genome and help predict what's the cause of the disease in humans. Just a couple of weeks back, we released AlphaFold 3 for everyone. It's multimodal. We have gone from attention-based model to the diffusion-based models, and AlphaFold 3 can do also DNA, protein binding, RNA protein binding, all the modalities of molecules, and predicts the structure. So it is going to be a huge step forward for drug discovery and human health. And there's the AlphaFold server, which you can access, which for freely now, and you can run and do your proteins. There is no questions asked. As long as you're not making money out of this, it's only for academic use. It's available. AlphaFold server is available freely. And with this thing, John Jumper is one of my colleagues, and Demis is, of course, the CEO of DeepMind. They got a Nobel Prize in 2024. It was a big step forward, and it's the recognition of the Nobel Committee about the impact that has on human mankind. So that's essentially what I had. I think we all need to come together, essentially using AI safely and really for the purpose of impacting humanity. Thank you very much.
Thank you, sir, for connecting with us through hybrid mode and delivering this interesting, innovative, and thought-provoking talk. As we all know, Google DeepMind has developed these AI tools like SynthID, GraphCast, and AlphaFold, aiming to prove humanity's well-being and scientific progress. The AI tools that you spoke about emphasized on how AI helps to better the lives of mankind. Thank you so much, sir. Sir, can you take a question or two from the audience?
Absolutely. Your volume, the audio is not so good, so I don't understand you very well, but it's better if I can get it. I'm happy to answer any questions.
Anyone has a question?
I can't hear the person at the back speaking. I'm sorry. The volume is not coming through.
Hello, sir.
Yeah, now I hear you. Yes.
Thank you, sir. Thank you for joining us online. And it is such a wonderful presentation. As I closely work with AI in my project, and I can closely relate with all the things which you have told. I have one doubt, sir. It's like with the large number of data sets being generated in healthcare and in various sectors, how does the large language model use the reinforcement learning to cluster the labeled and unlabeled data sets? Like how do you use actually the K clustering model, the random foresting model, and how does the correlation models on Gemini work?
So first of all, the clustering and all the clustering, K clustering, PCA, all the random forest models, these are all statistical models. So these are machine models which are basically looking at what is the pattern, and you take a decision. What we are looking at is more or less as a transform based models called these are large language models that do not really do the way the classical random forest and K clustering, K means clustering, etc. These are neural nets. They have huge number of parameters, billions of parameters. So if you read the paper, Attention is All You Need by Ashish Vaswani, that is the fundamental paper which really we use to do it. So you don't have to do it. The way it works is, I'll give you an example. Okay, if I say I crossed the road to reach the other bank and I crossed the river to reach the other bank, if you take those two sentences, right? So the difference between the two sentences is road and river. If I say I crossed the road to reach the other bank, it means that I went to another financial institution which is on the other side of the road. It's to reach the other bank. If I say I crossed the river to reach the other bank, it means I crossed across the river and reached the river bank. The whole two words are completely different. So the context for these two sentences is given by river and road. Road and river will give you context for that bank. So basically, when you do these attention-based models, the model knows that you need to put attention on the word river or road. That is my point where I need to put attention so that I get the context for bank. So that is how the whole model works. And then you go through this context-based modeling. So as you read through the sentence, as you read through your text, you know which part of your text you need to put attention and not on which part. And how you do is you convert this whole sentence into a vector, and from the vector you calculate what is called a cosine dot product. I'm getting into the weeds here, and you calculate the distance of that particular bank in the hyperspace, and then do all the kinds of mathematics around it, and then do it. So it is not random forest, it is not K-means clustering, it is an attention-based model. And what diffusion-based models is, which is the current era, we are graduating from attention-based models to diffusion-based models, is we take the model with the text, we distort it and rebuild it back, and based on how we rebuild it back, it creates a special kind of, you add creativity into it. Most of the images that are being generated, they're all RF diffusion based models, and they're completely different. So this is a completely new class of models, not like random forest, K-means clustering, PCA, the supervised learning, unsupervised learning. It's little bit more, not little bit, substantially different from what are these. So I think you should not see it from that context. You should see it completely from a different context. Did I answer your question?
Yes, sir, absolutely. And sir, how does the correlation models on Gemini work, sir?
So what do you mean by correlation models? These are not these are models which are available. These are huge billions of parameters model, and you just give it text and it uses the transformer architecture and predicts the next, whatever you based on what you want, it predicts the text. So I don't understand by what you mean by correlations.
sir, let's say like we give a prompt to Gemini, and then based on that prompt, how does the Gemini means actually sense the context out of our prompt, sir? So
Yeah, so the prompt is basically you have a model and the prompt is taking the context and you give something to the model. The transformer model itself, based on this, it converts into vector. It does the, you need to read the paper, attention is all you need. And it focuses on the attention part, like I gave you an example, a simple example. And then with that, it knows what it needs to do. Originally, we built it for translations because translation is a similar thing. I say something in English, I want it in Telugu or any other language, then basically I need to understand the context of what I'm doing in English, what I'm saying in English, to the same text in English, and you need to pick up different text. Essentially the same thing, but here you do it in the same language or in the same text. So you take the context of what I'm saying, and I look through a huge model. I have a corpus of text, and I extract some bit of it and give you an answer, kind of a thing. So that is how it works. It is not like I'm sifting through a lot of data. It's all in there. That's exactly from the Go example which I gave you. It is more based on pattern based rather than enumerating everything that's possible, because everything that's possible is so huge and you can't do it in a second or two. I think we can have a separate discussion. Maybe it takes too long. I can explain, and I think you should read the paper which is freely available. Attention is all you need. That's the original paper you should read. I can't hear you.
hello. Yes.
Yeah.
Thank you, sir. Thank you for your answer. And so one more thing, it's not related to the discussion which you mentioned. Like as we use AI more and more, the one problem which I face with Gemini is the file model attachment. As like currently, the file model attachment, like it's through the Google Drive. The Gemini can't directly access. Like if we put the file. So if you can
Yeah,
just
I think that is all operational part. I think that's some specific how we do what we do. I think that's a different discussion.
yes, sir.
Let's talk about more about in a general way how we are using AI. Of course, you can do it over Drive, and there are multiple APIs, etc. That is really going into the weeds, and I think it's not interesting for many people. I can have a separate discussion.
Thank you, sir. May I request you to just stay back for a second, sir? We would request.
Yeah, please. I'm available. We can ask questions.
Okay. We would like
please.
the distinguished speakers
please
to
ask
have a
questions.
photo with you, sir.
You have me.
Oh, before that. Yes.
Excuse me, sir. Can you hear me?
Yes, I can hear you.
Yeah,
Please.
it was wonderful to listen to your talk on, especially on AlphaFold, and that is really going to be a big revolution in the humankind considering its applications. So recently I have started my project on the molecular biology, especially for the crop production point of view, especially to understand the ripening process in the plants and how we can stop the, like as you mentioned, rightly pointed out, the crop production as well as the insecticide, how to avoid such kind of problems. So one of the problem that what we have faced is the transmembrane proteins, and as such, the AlphaFold 2 and 3 mainly talks about the structure which are already available, and based on that it is able to predict the new structures based on already what is available in the literature. Now the transmembrane protein, unfortunately, that is where I started my project, and those structures are not available, and it produces some approximate structure. Now, how I can validate that particular transmembrane structure? Now, I went through two approaches. One is the AlphaFold model, other one is a David Baker approach, and both of them, they got the Nobel Prize this year. And I could see that these two structures are different. So, what do you comment on the structural prediction ability for the proteins? The literature data is not available.
Yeah, so in general, the accuracy of AlphaFold is considered to be the best right now. That is what we see. AlphaFold 3 is, which we released last week, is amazing. Means it's one of the most accurate right now. I know X-ray crystallography data that comes out is benchmarked against AlphaFold. An AI model is considered a benchmark for X-ray crystallography. It never happened ever. But when I look at Baker's models are basically Rosetta fold models, and there is also some fold like OpenFold. Meta put out the ESM models, so they all are slightly different, and most of them. And if I look at AlphaFold 2 and ESM and OpenFold, OmegaFold, IGFold, Rosetta Fold, all these models are more or less attention-based models. AlphaFold 3 is a diffusion-based model. I said we are graduating from attention-based to a diffusion-based model, so it's way more accurate. It's pairwise heavy. It is less on MSA, and a lot of other things are different. But I think the end of the day, the AI is a tool which is giving you an input. It's telling you this is how it looks from the machine learning standpoint. We need to validate that, and that's why even now, and thankfully so, you cannot launch a drug based on in silico work. You have to run it on humans, and you need to understand whether the drug works in really through going through phase 0 to phase 3 clinical trials and launch your molecule. So you have to go through it. So these are all supporting machinery. Like even if you go back before AlphaFold came in, you used to do the X-ray crystallography data. You used to take a protein structure.
Yes.
Is it the Bible? Is it the absolute truth? No, protein exists in multiple conformations.
Yes.
And you've just captured a snapshot. You need to study the dynamics. How do you study the dynamics? It's very hard. So these are all tools you can use, like another tool that comes in, and you need to really understand and do a ton of other experimental work. The thing about AlphaFold is this tool is so powerful that you can validate this much more easily. You can trust the tool way better than you can trust any other tool. And David Baker also got a Nobel Prize, and Baker has put on so many other models in there. I have used them. I check against and benchmark against AlphaFold. So we are doing this, and it is not that we are competing. At the end of the day, we want to build the best model which is useful for humanity and give it for free. That is the most important part here. And so we never monetize AlphaFold. We are not doing any of these products which I spoke. All are available free. They're available for people to use, and hopefully it will be useful for humanity. That is the whole background and the context we are using. And yeah, we can go in why transmembrane proteins, whether they're correct, they're not correct. That is a very detailed discussion which you need to know what kind of parameters used, what happened, which databases, genetic databases using to build the models, etc. I think that's all refinement. But overall, in general, it is considered the current state of the art.
Yeah. Thank you for the feedback. Fantastic. Yeah. So thank you.
Sairam sir, wonderful, really amazed at the power of the technology that you demonstrated across different disciplines. One question I had, because coming from a materials science perspective, you did say that there is tons of materials that have been predicted, and also with the LLMs been able to develop synthetic routes as well. So if I want to kind of develop say for example a new material, I initially, when I do an experiment in the lab, initially I don't look at the kind of process optimization. I try to make the material first and then see how scalable is it, how cost effective, how useful, and all those things. So there is some kind of a optimization that the material synthesis goes through. So when you say that you have already kind of developed synthetic routes for these materials, what is that process parameter, or what is that optimization factor that has been put inside the algorithm? So what is it optimized against? Is it optimized against the structure to get the best structure, or the most optimized structure, or is it optimized against the availability of the raw materials, or is it optimized against the cost of it? How scalable can it be? Is it just wanted to know?
So the most important attention here we have put in is in terms of the stability of the material, because if it's not stable, it doesn't make, and we are not focused on whether it will be cost effective, because I believe even today, whatever is expensive will go down in cost when you look at in manufacturing of scale. The cost can always be brought down. There will be a lot of innovation, that's fine. But coming up with the first unique material is the fundamental step. For if you take lithium ion batteries, the lithium ion is now the costs are going down dramatically. Now, if I come up with something better than lithium, which is doing better things than whatever lithium does, it's a big step forward, and it might be expensive at the beginning, but the cost will go down eventually. So the focus here is stability and the functionality of this molecule, of this material. So if you look at it, there are 400,000 stable structures in the database. 428,000. They are possible. Means if I build a structure of that, whether that particular material is functional or not is again context dependent on what industry I'm applying in, but it should be stable. It should be available it should be stable. It should not just vaporize into air and things like that. And I think that is what we are focused on, mostly on the stability part, not on any other aspect, because if we get the stability part correct, then everything else falls through. Again, going back to the root of application. So if we can catch the root, everything else unfolds from there.
Can I ask two questions? So first question is related to the stability. Now the stability is of course temperature dependent. So does this model also can predict the stability at say 1000 degrees centigrade or 2000 degrees centigrade?
So stability is normal range of 20 to 35 degrees centigrade. That is what it is. Or I don't know the exact numbers, but stability is defined from what is available. Like you're holding a mic, the mic is stable. It's not breaking apart in your hands. That's stable. Of course, if I put it at 100 degrees centigrade, I don't know what happens. So in normal conditions, normal temperature conditions, it should be stable. That is the definition. Obviously, if I put at 0 Kelvin, everything will be stable because there is no dynamics. Everything is frozen, so it will be stable. So that is not the definition of stability.
Oh, so you mean room temperature? Okay. So second question is this alpha. If you compare like alpha 2, alpha fold 2 and alpha fold 3, okay, what is their accuracy in predicting the structures which are determined by NMR?
So I don't have the number specifically, but I have known there is a product called Pulse or Polar. I forgot the name, something with P, where they verify whether the NMR structure is in congruence with what AlphaFold predicts. So AlphaFold is the benchmark right now. So even if your NMR comes out well, because NMR is basically looking at the proton inversion and all this, there's a lot of errors that come in this experimental setup. So AlphaFold is considered the benchmark. It should have not have been like that. Always theoretical methods were being benchmarked against experimental methods, but now we have flipped the coin. So I can't talk about specifically on what the predictions are, but because it's based on the system and everything, usually the prediction of AlphaFold, and there's something called PLDTT scores. We predicted local difference distance test. It's some kind of a confidence and predicted alignment error. The two variables we put, which tells us that when AlphaFold predicts, it tells you what confidence it has with regards to whether that structure is correct or not. So there's a confidence measure that puts on each atom there is, and that tells you which part AlphaFold is confident and which part is not. And that very well correlates when we have a crystal structure where we have not resolved some loop, and you will see that AlphaFold also doesn't know where it is, just generally put something and it's put low confidence. That correlation I've seen. Again, there's a lot of, you should go into every specific protein and see how it works.
Thank you.
Thank you, sir. Thank you, sir.
Yeah, I'm most welcome. Thank you very much for the opportunity. And yeah, I'm happy if people reach out to me by email. I'll try and answer the questions if they have any.
Thank you, sir. May I now request Dr. Ravi Kishore, co-convener, and Dr. Smaran to please invite the dignitary speakers onto the dais for a photo session. Speakers. Madam, we request you to come onto the dais for a photo session. Thank you. May I request HOD Madam to thank you. Sir, just give us 2 minutes. We will, yeah, we will connect. Thanks. Sir, excuse me. There is a token of love from the Department of Chemistry as a memento, which we would try to send it to you, sir, in the due course. Thank you, sir. Thank you. Yes, ma'am. Yes, ma'am. We were, it's actually in the department. We will. Thank you for connecting with us, sir. Sairam.
Sairam.
Let us now break for lunch. The lunch would be served at the venues as mentioned yesterday. After lunch, let us assemble at 2:15 p.m. for demonstrations of student clubs, along with poster presentations of the undergraduate, postgraduate, and PhD students of the Department of Chemistry, Sri Sathya Sai Institute of Higher Learning. This post-lunch event is organized at the main campus lawns, where the photo session was held yesterday. Thank you. Sairam.